Hey, welcome back. So this section is a big one, really exciting stuff. I mean, exciting's relative. We are, talking about databases, but I do have a party hat here to celebrate. Yeah, so let's see, what are we talking about here? This course has been, so far, all about data in basically one table at a time. Kind of self-contained, basic data, nothing all that exciting, and nothing very complex. No data that is related. But of course, in the real world, all of our data, or almost all of it, is related. We don't have books on a website without also having things like reviews and customers and, shopping carts. We don't have cars on their own. We might have cars in our database, but then we might have salesmen and dealerships and all the other things that go along with it. Or like on Instagram, you don't have just photos. We have users, photos, comments, tags, likes, followings, relationships, all this stuff that's related. So this is a turning point where one of the turning points where we start to work with multiple tables that are connected. So we're going to talk about how data is related and then how to implement those relations using multiple tables. And some of the buzzwords, some of the big things we're talking about here are joins, foreign keys and primary keys, which we've kind of seen before, one-to-one, one-to-many, many-to-many relationships, lots of stuff. But like I said, this is the first of a couple sections focusing on related data. And the other thing that you may want to celebrate is that we are done with our books. Done with the books data. You can totally go burn the books if you'd like, throw them off a cliff. We're done with that. We're moving on to bigger and better things, inching closer to our Instagram data at the end of the course. Okay, have fun, and don't forget your party hat, because I didn't. Yeah. Okay, welcome back. So we're finally here. This is a bit of a turning point in the course. Really important section, not to scare you too much, but really fundamental to how SQL and MySQL are used in the real world. So this is a section all about relationships and also something called joins, which we'll get to in the second part of this section. So let's focus on the relationships part first. So far in this course, we've been working with very simple data. Things like books or users, where we only have a couple of columns per table. And that's been by design. We need that simplicity in order to focus on what's important, to isolate the different features that we're talking about, whether it's functions or logical operators. It's much easier to teach those when we don't have 20 different tables to worry about, and we can just basically drill down into one table and focus on that. But that's typically not how the real world works, where, we might have a users table, but there's no site that really can just get by on having users unless it's featureless. There's plenty of other things that need to go along with users, whether it's comments or likes or tweets or posts or photos or any sort of, order, transaction. There are all these different things that we could have alongside users. So we've been working with simple data.
But that's about to change.
Real world data, unlike what we've been working with, is really messy typically and interrelated. There's a lot of connections between data. So some of those things I talked about with, let's say, users, if we're working with just a simple blog site, so nothing like a Facebook or a complex social network, just a simple blog, we still need to have user data. We need to have information about posts, blog posts. We also need to somehow keep track of comments and then tags. And that can get pretty complicated already, not to mention things like advertising and tracking not only ads on their own, but how ads are related to users and what users are clicking on and not clicking on. There's so much data that just from a simple blog site, something that may not seem that complex, there's so much stuff that we could store. So we're going to focus on how we work with interconnected data in the next couple of sections. So we're no longer focusing on one table. We're going to see how do we work with two tables or three or four that are related. So not just tables that exist independently, but tables that reference one another and are interconnected. So let's get going. And the first thing that I want to do is go back to our books data. So remember our books table. Don't worry, we're done with it. We're not going to be typing any books code. But on its own, it was really simple. We had a books table with author first name and last name, a book title, released year, a page count, in a stock inventory, I believe, a stock quantity. And I think that was it. So again, on its own, that just represents a single book. but you can't really do much with that. But if we were running a sort of book site where we sold books, at a minimum, we would need to keep track of things like versions. So we didn't even talk about this, but there's often multiple versions of a single book. If you go on Amazon and you look at a book, let's say Harry Potter, the second book, Chamber of Secrets, well, there's going to be the initial British release, the UK version as a hardcover, and then there's a paperback, and then there's the American version, and then there's a paperback. There is a full color illustrated version that came out relatively recently. It looks pretty cool, that has these giant illustrations. It's the same title. How do you keep track of that? Is that a different table? Or do you just make a separate book for every one of those? But if you do that, then how do you make sure that they're connected? Because when I go on Amazon and I look at the hardcover, it also will show me below, some people also buy paperback version, or it's also available in, 25, 40 different languages. So there's all sorts of things to worry about just with versions. But then we have authors. Well, that might seem straightforward. We have an author, first name and last name, 2 columns on our books table, but that's not sufficient when we have multiple authors. So some books, a lot of books have multiple authors. What about if it's a research paper that we're selling or a journal that has dozens of authors potentially? So there's a lot of things to keep track of there that we can't really do right now. We only have room for one author in our columns. Then a whole big thing is customers. If we're doing a bookshop online, books on their own is great, but we also need ways to keep track of users, or customers is what I'm calling them in this case. So customers on their own also can't do that much, but we might keep track of their email, login information. Of course, we wouldn't just store their password directly, but for simplicity's sake, let's say we're keeping track of password and email so that they can log in. And then there's a whole bunch of other things. Orders. So if customers want to order books, how do we store that? We need to create a new order, and it needs to be associated with the customer who created it. It needs to have address information maybe. It needs to have the contents of the order. Are there books? One book? How do we support that? How do we handle that? What about if we're working with dates and times and we need to keep track of when a return period expires? So we need to have an order date and then keep track of 30 days or 60 days after that or whatever it is. Then we also need to store or somehow keep track of the transaction information. Addresses for billing address, not only shipping address, the type of shipping, the billing information. There's so much to store. And then a whole other thing is reviews. So if we go on Amazon or pretty much any book site, any book that you look at will have dozens or hundreds, sometimes thousands of reviews. So we've got reviews there, ratings, the number of stars, but then also a title for the review, and then a caption, and then the actual content of the review, which may be 10 characters, I hate this book, however many characters that is, or it could be a giant paragraph, someone's love letter that they're writing to a book. So how do we account for all of that? And then the last thing that we'll talk about are genres. So you may think that we could just get away with storing this in a book, which we absolutely could. We could just have one genre, but many books don't cleanly fit into one genre. We might have a vampire novel that's also historical fiction because it's set in Victorian period England. Or we might have, a sci-fi book that has elements of fantasy, or who knows, you can have all sorts of, cross-pollinated genres. So only assigning one genre might not be that useful. We may want to have a bunch more. And in fact, on Amazon, you can see there are books that will have 2 or 3 different genres or different tags associated with them. So what I'm trying to show you here is that we were working with books on their own, but in a typical app or a typical website that has to do with books, and a bookstore in our case, there's a lot more that goes along with books to make anything functional, to store any important information. And this is, maybe half of the tables that you would need to get away with, kind of the MVP or the bare minimum. There's still many other things. Something like orders, for instance, might actually need to be split into a couple of tables. We might need to have an address section or an address table. We might need to then have a separate billing table. We might need to have shipping. There could be all different tables that we could split it up into. So this isn't to say this is the end-all, be-all. This is just that there's a couple of other tables that we need to consider at the bare minimum. Okay, so we'll stop here. In the next video, we're going to identify some of the different types of relationships between data. At a high level, what are the different types of associations? And I'm back. I totally forgot to show you this. Even though I wrote a note to myself, I totally skipped this. So I'm back after recording this, adding this to the end. I want to show the schema diagram that I really think highlights how messy data can be. So I think I showed this early on in the course. This is just a potential schema for Facebook, and it's definitely incomplete. It's maybe a tenth of the number of tables that Facebook has. But you can see, just to store basic things like events and users, we have Facebook event, we have event membership, which is related to RSVP states, which is also related to venues, which is also related to groups and to workplaces and to Facebook profiles, and it just goes on and on and on. So what I'm trying to show you is that data can get messy. And in fact, here's another super intimidating schema. This one is a little bit crazy because it has to do with storing protein database. I saw some article on IBM and I believe MIT. Unfortunately, it's a very low quality image, so you can't actually see the tables. But each one of these little rectangles is a separate table, and every line is a connection between the tables. Now, this is the worst I've ever seen, the craziest, and I think that was the point, is that they're trying to just show you, they're never going to actually look at this to try and understand anything, but they're trying to show you how complex protein information is when you have all these different combinations and permutations for a given protein. Without going into too much detail here, this isn't a bio course, but the way that a protein is folded, the same structure, basically the same amino acids, depending on how it's folded, can drastically change the features, if you will, basically what the protein does, how it behaves. And so this is a way of documenting, using SQL in some way, the structure of a protein using a database. Okay, so not to scare you there, I just think it's kind of a powerful image. Although grainy, it is powerful to see basically some really messy, ugly, gross data that can be supported using tables. It just doesn't look pretty. But that's the important part, and kind of the point of this video is I wanted to get you prepared mentally for working with some more complex data, although nothing that looks like this. Okay, so we've established that in real life, data can be crazy, complex. Outside of the classroom, things aren't as nice as we'd like them to be. So we've established that fact. But now where do we start to kind of wrap our heads around how we represent complex data using MySQL? And the answer is we're going to start by talking about the relationship basics. So I know it sounds like marriage counseling 101 or something, but this is not. It's not that. This is about the different ways that data can be related. So if we have two tables or two entities, things like orders and customers, students and teachers, movies and reviews and users, how are they related? And there's a couple different ways. There's kind of these big, broad categories we can break relationships down into. And the terms that I'm going to use that you'll occasionally come across are three. There's the first one, which is a one-to-one relationship. I'm just going to go through all of them first before we talk about what they mean and talk about examples. So a one-to-one relationship, a one-to-many relationship, and then a many-to-many relationship. So the reality is that one-to-one relationships aren't actually that common, but perhaps another example, or one that I've recently used, is I had a customers table that had the basic information for a customer. So things like their username and their password, although again, you don't actually store the password directly, but username and password and email, and like registration date. And then there was a separate table where we stored all these details about a customer. So rather than storing 10 or 20 extra columns on the basic customer table, we decided to split it up based off of what was most commonly needed in the app we were building. And most commonly, all we needed was the username and the password and the email. But there was a whole bunch of other information that we were storing, so we created a customer details table. And that's a one-to-one relationship. One customer has their own row, one row, in the customer details table. And one customer details row is associated with one customer. So Colt Steel has a Colt Steel customer details, but there's no other user or customer that could be associated with it because it's a one-to-one relationship. Anyways, like I said, it's not the most common. What is the most common is actually a one-to-many relationship. And that's what we'll spend the most time on in this course because, like I said, it's really common. So here's an example. The relationship between books and reviews. One book can have thousands of reviews, right? Let's say Into Thin Air by John Krakauer could have probably tens of thousands of reviews by this point. It's been out for a while. It's pretty popular. But those reviews belong to that book exclusively, to one book. So the relationship is books have many reviews, but reviews belong to one book. So it's a one to many. So that's a really common classic example. Reviews or ratings and books or some entity. Okay, so then the next thing that we'll discuss here is a many-to-many relationship. And many-to-many is still relatively common, and the way that it works, it's what it sounds like. We have two entities, in this case, books and authors. And you could kind of speak through it. You could say, okay, books can have many authors. That's true. We could have two authors writing a book together, and those authors can have many books. There's no rule that says authors can only write one book. J.K. Rowling, however you say it, has 10 plus books. So it's a two-way, a many-to-many relationship. So hopefully you can see the difference there. Reviews and books. Reviews belong to one book. They're associated only with one book, whatever the book title is for that review. It can't also be the same review associated for another book. So that part of the relationship is one, right? And then we have the books to reviews, which is a many relationship. Books have many reviews. This is different because books can have multiple authors and authors can belong to multiple books, or authors can have multiple books. And the way that we represent this is actually a little more complex. So we're going to come back to it. We're going to start off in this section by talking about the most common relationship and how we represent that, which is the one-to-many relationship. So that's coming up next. Okay, so we talked about the three kind of common relationship classifications. And as I mentioned, we're focusing on one-to-many first. And we're doing that for a couple of reasons. One is that compared to many-to-many, it's a little bit easier to get through. It's shorter, but also it's more common and it's more central, in my opinion, to most of the development that I've done and that I see other people doing. Not to discount many-to-many, but we're going to get there. We're starting with one-to-many. So we're going to start with a classic example. Customers and orders, or this could be users and orders or users and carts, whatever the transaction is, but we're going to call it customers and orders. So two tables, and this is a one-to-many relationship as we talked about earlier. So let's say we have a customer, President Bill Clinton. That's our customer, and he can place as many orders as he'd like. He can have many orders, but each of those orders is associated with exactly one user, President Bill Clinton, there is no way to have two people associated with one order. So it's a one-to-many. So customers have many orders. Orders have one customer associated with them. So let's talk about, for our case, what data we want to store. And it's going to be very simple. I don't want to clutter it with a whole bunch of other pieces of information. We're just going to focus on the basics. So a first and last name for customers and an email. Now, in a real web app, we'd want a lot more information probably. We want to create a registration date when a customer signs up, maybe a last active date that we're storing, or date time. Password, somehow we need to store that. There's so many other things. Phone number, if we're trying to do two-factor authentication, lots of things. So first and last name and email, so 3 things per customer. But then we also, for orders, we need to store the date that an order was made. So it doesn't matter for our example if it's date or date time, but we'll keep it simple with date. So 2017/11/12 or something. And then the price of the order, the total amount. Let's say 99.99 or 20.50. So that's going to be a decimal. So we're going to have first and last name and email, which should probably be varchars. The date of the purchase, which will be a date time, and the price of the order, which will be a decimal. That's the easy part. The next question is, how do we store that? How do we represent it? And we could do it this way, which I want to make clear. I'm not saying this is a good way of doing it, but you could technically get away with doing it in one giant table. But there's problems. But let's first just walk through how it works. So we have first name and last name and email for customers, and then order date and amount. So we have, boy George, whose email is george@gmail.com. He was a very early user of Gmail. And then we have the order date, 2016 to 10. And that order was $99.99. So this is capturing information for one order. But then boy George placed another order, and we have duplicated information because we're storing, it's boy George, which I know boy is not his first name, but just let's go with it. And then George@Gmail again, and then a different date. This one was later in 2017, and then a different price or a different amount. So this stores the information that we talked about. We needed first, last, email, and then date of the purchase and price of the order. And so that's working. Same thing with George Michael, who has gm@gmail.com, bought something in 2014 that was $800.67. And then George Michael, same email, bought something in 2015 that was $12.50. Okay, so already you should be noticing we have a lot of duplication, right? Even though we are storing the information that we're supposed to store, there's a lot of duplicated data. And then we run into these two, David Bowie and Blue Steel, my cat. There's problems because they haven't placed orders yet. So we have their customer information. We have David Bowie, david@gmail.com, also early adopter of Gmail. And we have Blue Steel, blue@gmail.com. And they haven't placed orders, but they still have order date and amount as columns, and they just have no value. It's null. So this technically represents that fact that Boy George and George Michael have 2 orders each, and David Bowie and Blue Steel have no orders. So that's really not a great way of doing it. Yes, it works, but we're not only duplicating a lot of things, right? Boy George, George Michael, and if somebody shopped a lot, we would have tons of duplicated information, which is just a waste. But then also we run into problems where we have users who maybe haven't ordered anything yet, and they just signed up for the site. There's no reason to have anything to do with orders until they actually place an order. So it's much better to keep our data separated, because if we ever need to work with just customers on their own, which happens, there are times on a site where you don't care about orders, you just care about customers. Let's say when a customer is signing in. All that you need is to take their email and check it, and take a password and check it against the password field. That has nothing to do with orders. So why would we need to go through a giant customer orders table? And that's just a really silly example. But what I'm trying to show is that it's not just about the duplication. It's also that sometimes it's better to keep your data separate, almost every time, unless you're always accessing your data together. Like if the only time we're ever talking about customers is when we're talking about orders, then maybe you could put them together. But then we still have this problem where we have people who haven't placed orders, or we have duplicated data. So this is a bad idea, not a good idea, aka bad idea. So what do we do? Well, here is the simplest approach. This is how we express a one-to-many relationship. And it looks like this. So we have 2 tables, customers and orders. And customers have an ID field, and then a first name, last name, and email. And then orders have an ID field, and then the date, the amount, and then this is the crux of everything. They have a field called, it doesn't matter necessarily what it's called, but ours is called customer ID. And it's a reference to the customer's table. So whatever customer ID is in a given order is going to correspond to an actual customer who placed it. So let's dive into it a bit more. Here's an example. So I took the exact same data. We had 4 orders and 4 customers from back here, and I split it up into separate tables. And you can see, let's just talk about customers first. We have a customers table with an ID, a first name, last name, and an email. So we have boy George, George@Gmail, ID 1. George Michael, GM@Gmail, ID 2. David Bowie, David@gmail.com, ID 3. And then Blue Steel, blue@gmail.com, ID of 4. These are all unique, corresponding to exactly one user or one customer. And then we have our orders table. So there's an ID there, order ID, and then the date that an order was placed, and then the amount, and then the most important part, well, arguably the most important part, definitely the crux of the relationship is customer ID. So in this case, it's 1, which is pointing to this customer with ID of 1, meaning Boy George. So Boy George placed an order in 2016 for $99.99. Here's another customer ID 1 telling us that this entire row here, this order, is related to Boy George again. So he placed an order for $35.50 on 2017. And then we have George Michael, customer ID 2, matches this ID here. And he bought something for $800.67 in 2014 and something in 2015 for $12.50, which is the exact same data we had represented here. And then notice that we have users like David Bowie, or customers, David Bowie and Blue Steel, who haven't bought anything. And there's no extra data, there's no nulls. We have the minimum information that we need. We're not storing anything that we don't need. So we don't have extra orders that are created because they haven't created orders. We have separate tables. So this is the classic way of structuring a one-to-many relationship. And along with that, there are 2 terms we need to point out, which we have briefly discussed. And the first one is primary key. So remember this keyword we can type when we're defining a schema. We can say, and what we've been saying a lot is ID space int space auto increment and primary key. And the effect of that, what a primary key means, is that some particular column, in our case, this customer ID, is always unique. So we only have one customer with ID of 1, and only one customer with ID of 2 and 3 and 4. And that's really important because if we're referencing it somewhere else, like over here, if there are 2 different customers that have ID of 1, then this is useless because which one does it refer to? So it has to be unique. And then that's where the auto increment comes in, right? Where it will make it unique every time we insert a new customer. It will automatically increment this to 5 and to 6 and to 7. So there is no possible way we could have duplicate customer IDs. And then also here is order ID, which is also a primary key. It is the unique way of referencing an order. Now this is a bit extreme, but it's possible that we would have 2 duplicate rows here where basically an order was placed for the same amount at the same day by the same person. It's possible. And we would need to refer to them separately though. We don't want our database just to combine them. Maybe a user purposefully bought the same thing twice. They bought it once and then they realized, oh shoot, I really should have bought 2. So then they buy it again, same amount, same day, same customer ID. Well, the only thing that keeps those orders unique is our order ID. So again, these 2 are primary keys. They are the primary way of referring to rows in this table. It's what makes them, or it's not the only thing that makes them unique, but it is guaranteed to be unique. And then that brings us to foreign keys. And foreign keys are references to another table within a given table. So in this case, in our orders table, customer ID is a foreign key because it's referring to this ID of the customers. So primary key, foreign key. Customers does not have a foreign key in it. It's not referring to any external table, but orders has a foreign key. And that terminology is important. We'll come back to it a lot. Primary key and foreign key. And it'll also show you how you actually say in your schema definition that something is a foreign key. And the reason you would do that is to enforce that whatever customer ID is in here is an existing customer ID over here. Because what if we inserted something, an order and an amount with customer ID of 20, and we don't have a customer with ID of 20, most likely we don't want that to happen, right? We would want to bounce that back and say, hey, this is a problem. There's not a valid customer with that ID. And that's what foreign key, when we use that in our schema definition, it will enforce that. Otherwise, if we don't say that it's a foreign key explicitly, we could have customer IDs, all over the place that don't actually exist. Okay, so this is the schema that we've defined. Well, this isn't the actual schema, but this is the basics of what we want our schema to look like. Now we're going to implement it in the next video. All right, so we discussed our game plan for implementing the relationship, the one-to-many association between customers and orders. Now let's get to it. So we'll start off with customers, which is a little bit easier. So we're going to have an ID a first name, a last name, and email. And these three, the last three, are all varchars. An ID is an int. So let's start off with that. And I'll let you know, I have basically our data already written so that we don't have to spend time typing it out. You'll be able to copy and paste it. But I do think it's good if you go through actually typing the schema itself and just copy and paste the data in, because there's no reason you need to spend time, typing blue steel and all these email addresses over and over. Okay, so create table, customers. And let's just start by defining what we need. So we have an ID, we have first name, we have last name, and we have email. And as we said, these are all varchars, and we'll just do 100, and I'll copy that and paste it. Add my semicolon, and so we're almost there. We just need to figure out ID, and this should be review. We have int, and we could leave it at that, but it's best to add auto increment and primary key. And that's because, well, a couple things. One, it's a good habit to get into. At the very least, it can be useful for sorting things. But more importantly, we're going to reference this ID, customer's ID, in another table. And so we want to make sure that it's unique, like we discussed. We don't want to have, customer ID 2. We don't want any ambiguity as to who or which customer that's referring to. If we had two different customers with the same ID, that would be problematic. So we're going to make it unique with primary key and auto increment. Now, primary key on its own enforces the fact that it's unique, but we would have to manually enter it in. This should be review, but I would have to actually say something like insert into customers, and then what would I do here? Let's say ID, and I'll just do first name. I would have to manually go through and say, okay, this user has ID of 2 and a first name of Tom. And then the next one, I would have to make sure it was unique and do 3, or I could do 20 or 50 as long as it was unique. But I don't have to care about that ID if I put auto increment. So we'll do that. Okay, so that gives us customers. Let's make sure we add our comma there. And then next up, we have orders. And order has an ID as well, so that will also be a primary key. Then we have order date and amount. So let's start with those three. Create table, orders. And the first thing we have is ID. And then we had order date. And you might be inclined just to call it date, but that can be problematic because that is an actual data type. It would be like naming a column int or varchar. So we don't want to do that. So we'll call it order date. And then we have amount. Okay, so order date is just going to be a regular date. We won't worry with date time, even though I prefer date time. Just to make it simpler for us, we won't have to deal with the time component. So that's not what this exercise is focused on, so we're just going to eliminate that. So date, and then this will be a decimal. And for our purposes, let's say 8, 2, so where 8 is the total number of digits and 2 is the number after the decimal. So we'll start with that. Decimal, 8, 2. Order date is just a simple date. And then ID is an int. And we'll do the same auto increment primary key. But then that brings us to the last thing, which is different. We haven't seen this before. And all we're going to do is write customer ID. That is the name of the column. What data type is it? Well, it's just going to be a number. It's an integer. So we could just leave it at that if we wanted to. And I'll show you what that looks like to start. So I will go ahead and leave it at this. I'm not recommending that you actually run this just yet because we are going to change this, and I'll show you why in just a second. Okay, so let me add my semicolon in here. And then let's make sure we don't have any typos. The first thing I'll show you is that I'm in a new database. This is a bit of review, but it's been a while. How do I check the name of the database that I'm currently in? It's select database. So I made a new one. It doesn't matter. You could do it inside the bookshop. I just wanted to have a clean thing. We have no tables yet. So I'm going to make our customers table and see if it works. And then our orders table. Okay, perfect. So then I have all of this data down here. that I'm not going to type by hand. But if we take a look, it's adding how many users? 5 users. I added one who wasn't in our database already, or who wasn't on the table here, which is Betty Davis. So we have Boy George, George Michael, David Bowie, Blue Steel, and Betty Davis. So that's just going to insert into customers. Make sure that works. Let's do a select star from customers. Perfect. And then this is a trickier part where I'm actually inserting the orders. And if you notice, all that I'm doing is the date of the order, the price, and then customer ID at the end. And right now, there is no explicit association between customer ID here and ID here. All that I've said is this is a number. So it's up to me to put whatever I want in there. So let me show you. I'm just going to do that now by copying this and pasting it in. And now if I do a select star from orders, you can see we have customer IDs 1, 1, 2, 2, and 5, which is fine. That looks good to us because we also have users who go up until 5. But there's nothing stopping me from doing something like this. Let me just copy this first part. There's nothing stopping me from inserting something with, let's say, price is 33.66 or 67, why not? And customer ID is 95 or 98. There's nothing stopping me from doing this. And that's not, well, I mean, we could get by with this, right? We could just know that we're never going to insert something with a customer ID that doesn't exist. But because there is no association between customer ID and this ID, we can do whatever we want, which is usually not a good thing. So if I hit enter, now we have an order with a customer ID that doesn't actually exist with a corresponding customer. So what we want to do is actually add in a constraint here. So just like there's a primary key, we also can explicitly say something is a foreign key. And the easiest way, it's a little longer. It looks like this on a separate line, foreign key, and then in parentheses, we say the name of the field or the column we're referring to, which is in the orders table, customer ID. And then we have to say what it's referencing. So it's referencing, think of drawing this line up to ID. Okay, so we have customer ID up there. So we're going to do references, and then the name of the table, which is customers, and then in parentheses, the name of the field, which is ID. Oops, I lost it. Here we are. Okay, so it seems like a lot. But all that we're saying is, hey, there's this column that we already defined, customer ID, it's an int, make that a foreign key. And it needs to reference, remember foreign key means that it's referencing something external, something outside the table. We want it to reference the customers table, and in particular, the ID field. One small note I'll add, your keys don't always have to be IDs, they're almost always IDs, but you can get away with other things. Like I think we discussed this earlier, sometimes you want emails to be unique and you could make that a primary key instead. But IDs are easiest because they're short, they're simple, you can auto increment them, and it's 99.9% of the time what you'll use. So here we go. Again, just to go over the steps. You define first customer ID, and then, and just to clarify, you can call this customer ID, you can call this whatever you want. I gave it just regular ID, and gave this customer underscore ID, which is a convention when you have a foreign key to use the name of the table underscore the name of the column, just so that it's clear. And we already have an ID here. Okay, so we're taking this, making it a foreign key, referencing this field here. So to see the effect of that, we're actually going to need to drop our tables and start over. So it's just drop table, and we can do them both at once. So customers, orders. Okay, and now, how do we see our tables? It's a quick review as well. Show tables. Nothing. Okay, so I'm just going to paste this in again. We got our first table. Make sure we didn't screw up our syntax at the second one. Great. Only difference is this line here. Now, we're going to insert our customers again and insert our orders again. And if we do a select star from customers, you can see nothing changed. Do a select star from orders, nothing changed. Great. But then Now let's try and insert something else like what we did earlier. So I'm just going to copy this line again down below, and we're going to insert an order. We can keep the same date. Let's do June 6th. And our price will be 33.67. But our ID is going to be 98, which doesn't exist. Our customer ID is 98, which doesn't exist as a corresponding user or customer ID. As you can see, we only go up till 5. So if we try that, now we have a problem, which we didn't have before. Cannot add or update a child row. A foreign key constraint fails. And so basically it's saying I can't do that because the constraint you had said this was a foreign key referencing customer ID or customers in the ID field, and there is no customer with ID 98. So it's now enforcing that, which is great. And if we select all of our orders again, you can see it's not in here. It didn't make it in here. So we now have this, think of it as a bouncer at the door that is checking if there's a corresponding customer, which is useful. Okay, so that's what foreign key does. And I'll go ahead and end this video there. But we haven't really explored our data yet. So in the next video, we're going to start seeing how we can work with our data. How do we basically connect these two tables? We have them associated, but now how do I do things with them? How do I figure out who ordered what? Like if I look at orders right now, I have a customer ID, but what if I want the name of the person, the first name, or both first and last name, or the email? So that's coming up in the next video, and we're going to dive into a really important topic, which is joins. So that's coming up. Okay, so we've got this data in our database. We have two separate tables that are distinct. They have a foreign key. The orders has a foreign key referencing customer ID. But so far, we haven't actually done any queries. We haven't worked with our data. So let's try it now. So back over in Cloud9, let's start with a simple question. Let's look at our customers. Well, actually, let's look at our orders. And I have 5 different orders here. Let's say I want to find the orders that have been placed by Boy George. So how do I do that? I want the orders placed by Boy George. Well, we could do it as a 2-step process. So I would first say, basically find the ID of the customer whose name is Boy George. So we could do select star from customers where, and then we would do something like where last name equals George. Okay, so we get Boy George, george@gmail.com, and his ID is 1. Okay, so then we take that and we go to our orders table and we try and find, okay, where is in the orders table is customer ID referencing 1. So we're just going to do a select star from customers select star from orders where customer ID equals 1. And there we go. These are the 2 orders placed by Boy George. So that was a 2-step process. And we could simplify that, or we could at least do it all at once, actually using something that we touched on. We could use a subquery. If you'd like to try and do that, you can take a moment to figure that out, but I'm just going to write it down here. We would do something like this. So the 2 things we just did, let's just copy this one. We did this right here. Select star from orders where customer ID is 1. And then we also had select star from customers. So to put them together, what we basically want to do is find the ID of the customer where last name is George. Then plug that into here. So rather than hard coding it as 1. So it's going to be a bit long. So it's going to be something like select star from orders where, and then where is going to be long. So it's going to be a subquery. And we want to do where select ID from customers where last name equals George. Okay, so let's take a look. We need to fix one thing actually. Select star from orders where customer ID equals the result of this. Okay, so let's step through it. Start with this middle part. This runs, it selects ID from customers where last name is George, which is what we did up here. So when we run that, we're only selecting ID. So actually we could change that because we're only selecting ID, and it gives us 1. So you could think of this whole thing is replaced with 1. Actually, it's more like this whole thing is replaced with 1, which leaves us with select star from orders where customer ID equals 1. So let's test it out. And you can see we get the same result. But this is still not ideal. It's a bit cumbersome. And this is only if we're working with one user anyways. What if I wanted to see a synthesis of my data? If I wanted to see next to every order, so something like this, if I go up, let's do select star from orders. Next to every order, I wanted it not just to say customer ID, I wanted it to say the name of who made the order. So Boy George, George Michael, Betty Davis. And I wanted that to be printed here. So how do we do that? And this leads us to our next topic, which is joins. So joins allow us to accomplish that. The whole point of joins, which is sort of this buzzwordy, maybe intimidating, mysterious thing to some of you, the whole point of it is that it takes two tables and we can conjoin them in a couple different configurations. So we'll talk about what those are. That's the next few videos. But we can conjoin them, basically take the data from one and take the data from another and stick them together in usually a meaningful way. But I'm going to show you one way that is not meaningful to start. And this will be our first, most basic join that you probably will never use. I never have used it, but it's good to know. And it just looks like this. Select star from orders. We can do customers first. It doesn't matter. Customers, comma, orders. And that's it. So if we just select from both of them, what do you think will happen? I'm going to hit enter here. And we get this monstrosity. It's very long. And what we're actually looking at is called a cross join. I think I've also heard it called a Cartesian join. Like I said, it's pretty useless, but it's interesting to see. What it does is it takes every customer. So we have Boy George, George Michael, David Bowie, Blue Steel, Betty Davis. But then notice that, let's ignore the right half, just the customers. It goes from 1 to 5, and then it repeats. Boy George, David Bowie, Blue Steel, Betty Davis, and then Boy George, George Michael, David Bowie, and it keeps going. And what it's doing is taking every customer and conjoining it with every order. Think of it as almost multiplying them. So it's taking the first order, which is $99 with an order ID of 1, and it's sticking that next to Boy George, order ID 1, George Michael, order ID 1, David Bowie, same order, Blue Steel, same order, Betty Davis, same order, and then it moves on to the next order. So then we go back, Boy George, stuck with the second order. Second order. It basically, hopefully you can see what's happening. It's a lot of text to look at, but it's taking these two tables and just jamming every row, every possible combination next to each other, which is meaningless. There's no reason to do it. But I just wanted to show you it because it's the first and most basic type of join. So don't make much of that, the fact that you can do it. It's just good to know that you can, but we're much more interested in basically whittling this down to the stuff that we care about. So maybe the most obvious and meaningful way would be to whittle it down so that we only see where there's actually overlap. So where the ID of the customer is the same as the customer ID. So this would be a match, right? This is an order placed by Boy George. But then none of these are actually placed by the customer they're next to. But then we get down here and we have, okay, here's George Michael with an ID of 2, and he placed this order. So how do we whittle it down to that? And that's what we'll see in the next video. Sorry for the cliffhanger. Okay, so in the last video, we saw our first join, our first example, which is actually something known as an implicit join, which you'll see for a moment why it's called implicit. And it's also, in particular, it is a cross join. Useless, basically. So it just think of it as multiplying our data, cross multiplying. It takes every possible combination. So we have Boy George. Well, I don't need to go over that again. I'll bore you to death. So now we want to focus on whittling it down to what's actually relevant. I want to see the name, first name, last name, and email of every user who actually placed an order next to that order, not just every arbitrary order. I want the ones that they placed. And so we're getting sort of close. If we have all of it next to each other, now we just want to only select the rows where what condition is true, where our user ID is equal to the order customer ID. So it's just like any other kind of select we've done, where we just can add in a where. So it will be a select star from customers, comma, orders, where what is true. Where ID from the customer is equal to customer ID. So we could do this where customer equals customer underscore ID, but there's a problem, and maybe you've identified it. We have two IDs. Remember, we're just taking the customers table and the orders table and putting them together. So we have ID from customers and ID from orders. So what does this refer to? That's a problem. Fortunately, there's a workaround. It's very, very simple. All we have to do is prepend the name of the tables. So this should be our customer's ID, right? It's coming from here. And just to make that clear what's happening, we're saying where the customer's table dot ID, so where this is equal to customer ID. Now customer underscore ID, and I realize there's a lot of saying customer and ID over and over, but these are different, right? This is the customer's table ID. It's referring to this, customers dot ID. That dot means in the customer's table. And this is customer underscore ID, which is referring to this right here. So we don't have to say orders dot customer ID, but it's a good convention to follow to do that. Just to, whenever you're working with two or more tables, to be explicit about which table, or which row, which column belongs to which table. Okay, so we have this line. Let's copy it over. So what this will do is it's going to do this cross join, but only where the customer's ID, customer table ID, is equal to the customer ID of the order. So now if we do this, take a look at what we get. We have 5 orders, so we get these 5 different rows, and we have the corresponding customer who placed it. So Boy George placed this order for $99. Boy George placed another order for $35. George Michael placed these 2 orders, and Betty Davis placed this one order for $450. So you can see we have customer ID over here, and it's matching the customer's ID. And of course, we could condense this a bit, so maybe we don't want star. Maybe we want first name and last name, and then order date and amount, and that's it. Just like that. So let's try it. And now we get a more condensed table that has that information. Boy George, 2 orders. George Michael, 1 order. George Michael, another order. Betty Davis, another order. So what we've just done there, we have joined them together using what's known as an implicit inner join. So I'll write that here. Okay. And that's what we did up here as well. So this is just a more refined one because we're not selecting star. We're only selecting a couple of things. But we've joined them where they match, if that makes sense. So I have a simple diagram. It's very, very ugly, but a simple diagram to show you. And I'm sorry it's so ugly. It was very difficult. Filling in this shape here is not a circle, and the slides tool I use doesn't let you draw weird shapes. So you have to do circles. So I'm sorry. I really am. But what's happening here is that we have 2 tables, right? Customers and orders. And what we did at first was select everything, combine them, and just take everything together. But all that we want to do with an inner join is take the inside where they overlap. And that's what we did. We went from this monstrosity and we whittled it down to where the customer's ID is equal to customer ID in the orders table. and we get this right here. Okay, now I said this is implicit, and that's because there's an actual explicit syntax. There's a better way of doing this. And when I say better, it really means that it's more conventional. If you're not familiar with that, it means that it's, think of it as like an unwritten rule that developers follow. They think it's cleaner, it's more easily understood to do it this way, which I'm about to show you. So I'm going to write, what did I do? Here we go. I'm going to write comment explicit inner join. And this will be the first time we see a new keyword called join. So we're going to do our same select star. We'll start with this one from customers. However, we're not just going to do comma orders. We're going to select star from customers, and then we're going to add join orders. So we have some new syntax. I'm just going to type it all first. And then we're going to tell it where. We're going to join on customers.id equals orders.customer ID. Okay, so if I copy this and I run this, it does the exact same thing. And if we want to, of course, we could refine this more, just like we did earlier. So instead of selecting star, let's do the same thing where we select first name, last name, order date, and amount. Okay, copy this over. And now we get the same table, and just to prove to you that it's the same, there you go. Can't even see a difference when I just hit enter, and it looks like the same thing as here. Okay, so this is still an inner join, but this time it's explicit, and it's really only explicit because we're writing the word join. So when we say join order, so we say from customers, join orders on this join condition. So take the left and the right, so it's customers and orders, these two circles basically, and join them, create the union table where customers.id is equal to orders.customer.id. So where the ID from here matches the customer ID from here, take that overlap and make this table for us. So I know it's a lot that I'm talking about here. And the term inner join and explicit inner join, implicit inner join, and we're going to next talking about right joins and left joins. It can't be overwhelming. So all I want you to focus on is the key idea here, that we are joining data together based off of a condition, right? And we could join it off of some meaningless condition too, just to show you. So if we go back to this really ugly cross join, where it takes everything and joins it together. So if I wanted to, there's no meaning to be garnered from this, but I could join it where the two IDs are the same. So not customer ID, but I could say where customers.id is the same as orders.id. So let me just show you that now. And I'll just comment this as arbitrary join. Don't do this. But we could do this. We could select star from customers, join orders on, and I'll just say where customers ID equals orders.id. There's nothing stopping me from doing this. And as you can see, I just end up with this new table that has matching IDs. So we get, let's take an example like George Michael. So George Michael is now matched. He has an ID of 2. He's matched with the order of ID 2. It doesn't matter that it was placed by customer with ID of 1, which is Boy George. So I'm saying that we can just join things on arbitrary conditions. However, what goes in here is you're filling in a foreign key matching a primary key in another table. So primary key is the customer's ID. The foreign key is the customer underscore ID in the orders table. And then the last thing that I'll wrap up with here is, does the order matter? So if we go back to our cross join, what if I reverse the order? So I started with customers, comma orders. And so we get customers here and then orders tacked on the right. So what if I switch it? Orders, comma, customers. And you can see, well, it looks very similar, except, well, it doesn't look similar. We have the same data, but it's been switched. So we start with every order first, and then one customer tacked on to the end, and then every order again, and then the same customer. So the order does matter in a sense as to how your data is presented to you, but it doesn't matter in the case of a cross join or in the case of an inner join. It won't actually affect the result. It just affects what is printed out, what it looks like. So let me show you. If we take this same, we've got a lot of them going on here. Let's take this same one here. This is kind of the most useful join we had, right? Where we had the name and the order date and the amount. If I switch, and I'm just going to duplicate it so that we have the original as well. If I say from orders, join customers on, and we can leave this either way, but let's say I do that. So I'm selecting from orders with joining customers onto it, and I hit enter. Nothing changes. And that's because we are picking our data, individually from up here. Now, if I just did a star, it would look a little different because you can see we're actually getting order first. So order ID, order date, amount, and then customer. And if I switch that, it would be the other way around. That doesn't really matter. It's just, orders. But you can see now we get customers and then orders. All right, so this has been long and a little difficult, I imagine, especially some of the syntax or keeping the jargon. What I do want to say is that basically when you're joining things, don't do implicit joins, which is what we have here. It's better to do it explicitly this way. So something like this or this, where we have select something from a table, join on another table on a condition. Okay, so that is kind of the bread and butter of joins, doing an inner join, but I'm going to show you a couple of other examples. That'll be up next. Okay, I hope you're still with us. I really hope it didn't put you to sleep with the last video. These are getting a little too long for my taste, significantly too long, so I apologize for that. But there's a lot to cover here, and there's no great place to break it up. However, we are done with kind of the long slog of explaining joins. Now I'm just going to show you another type. So inner join is what most people end up doing. That's a big generalization, but it's what I end up doing most of the time. But there are other types. And the next one that I'll show you is called the left join. There's left and right. They work very similarly, so once you understand how one works, it makes it easier to understand the other. So what we saw so far was the inner join, where we take one table, A, and another table, B, and then we select all the records from A and B where the join condition is met. But there's another type of join. Before I get there, I want to show one other thing. If we go back to any of our joins that we had, let's take this one here. So this gives us our nice little table with Boy George and his orders. We have George Michael and his orders and Betty Davis in her orders. I can do just any regular MySQL functions and things that you're used to with this data. So I didn't make that very clear in the last video. This isn't some special table. We can do whatever we want. So I could do something like group by, or let's start even simpler. I could do an order by. Let's do an order by, and let me actually move this so we have a record of everything we've done. So I'll scroll down, getting fancier. Here we go. So we can do an order by amount if we wanted to. And now we have from the lowest order up to the highest order. Or we could order it by order date. So that's one thing we can do. But we can also do things like group by. So maybe, let's say this is something we actually might want to do, is take all of our orders and group them by who ordered them. Okay, group them by who ordered them, and then take that and find the average amount they spent, or the total amount. How about we start there? Let's identify the biggest spender in our entire database, which is pretty easy to do if you just look here and add things up. But let's say we had 10,000 records. How do we find the biggest spender? So we'll group by, and how do we group them? Well, we want to group by our customer, right, who placed the order. First name could work, but that assumes that we only have one Betty or one George, and we might have George Michael and George Foreman or something. So that's not going to work. We could do first name, comma, last name, but we still could have people with the same name. So it's better to just group by something we know is unique, like customer ID, just like that. And let's be explicit, orders.customer ID. So group by that. And if we hit enter, remember when we do group by and we don't actually do any math or any functions on it, it looks like it just cut data out because that's just how it prints things to us. But now you can see that we have grouped by the customer ID. So I know it's hard to see because we're not displaying customer ID, but remember that customer ID is unique relative to every user. So we're basically grouping by customer. Hopefully that makes sense. You could make it a bit clearer if you did something like this. What we've done, and let me get rid of the group by briefly. What we've done is take these customer IDs here that we weren't showing and just grouping these two together, and this one on its own. But we're not actually displaying that. Okay, so we can group by that, like we did. And then all we want to do is total together the amounts. So rather than just amount, let's do sum amount. And I'm going to clean this up a little bit. And let's give it an alias as total spent. Just like that. Now let's try it. Cool. So we can see Boy George spent 135, George Michael 813, and Betty Davis 450. And then lastly, we could order by total spent. Move our semicolon. Now you can see, and actually let's do descending. Now you can see, okay, George Michael is definitely our biggest spender. 813.17 cents. Perfect. Now, order date doesn't really make sense to have in there, so because we have multiple orders, and it doesn't make sense just to show one, so maybe this makes more sense. There we go. Okay, so I just wanted to show that you can still do typical things that we're used to with the results of a join query. It's not some special alien type of a table. Now that brings us on to the left join. So another way of joining our data. Here's the ugly diagram I tried to make. It's a little better. The colors are still awful. I'm sorry. So what does it do? Well, it's going to take everything from the first table. So if customers is our table on the left, it will take every customer. And then on the right, it will try and match, or it will match any, or it will add any matching records from orders in our case. So these diagrams, just talking about it like this, I find isn't that helpful. But basically, think of it as it takes the union of where they match, just like inner, but then it also does everything from the left table, from customers in our case. So let's test it out. Over in Cloud9, I have a comment here for left join. And let's go take one of our joins that we did earlier. Like, let's do this first one. And this was an inner join. And one thing I didn't mention is you can explicitly write inner join, and I'll show you. It does the exact same thing. If you leave it off, it's implied that it's going to be an inner join. It's the most common type. What it does, as we know, it takes customers where their ID matches customer ID, and that's all we get. That's the inner part that matches. Now, if we change this to be left and select everything, you'll see we get a couple of differences. So we still have, it's kind of ugly to look at, I'm sorry. We have Boy George in the order he placed, and Boy George another order he placed. George Michael, 2 orders that match. But then we have 2 users who never placed orders. David Bowie and Blue Steel do not have orders. And so we end up with David Bowie, Blue Steel, null, 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 null for the orders portion, and then Betty Davis in the order that she placed. So we have customers on the left, orders on the right. We're taking everything from customers. So that's why we end up with David Bowie and Blue Steel. And then we take the intersection as well, where there is an applicable match. So for David Bowie and Blue Steel, there isn't one, and it fills in null. But for Boy George and George Michael and Betty Davis, there is a matching order. So I know it's kind of difficult to look at or understand, but think of it again. We have customers, and we go through at the beginning. Okay, Boy George, is there a matching order? Yes. This one here, right here, and this one. So put those together. George Michael, ID of 2. Is there any matching orders? Yes, there's 2. Put those 2 together next to George Michael. David Bowie, is there a matching order? No. So just put David Bowie because it's a left join. If it was an inner join, then David Bowie and Blue Steel don't show up. But it's a left join, which means we're taking everything from the left table. And it works perfectly. Well, depending on what you're trying to do. So that brings us to the question, why would you do this? And before we get there, I'm going to just clean this one up again so that we can see it a little bit easier. Let's only select first name, last name, order date, and amount, just like before. So that brings us again to the question, why would you do this? Why would you want to have excess information like David Bowie and Blue Steel? And it depends on what you're doing. And in this case, maybe previously I wanted to see, okay, all the orders that have been placed and names next to them. But now what if I want to tabulate the high spenders on our site, but I want to include people who haven't spent anything. So I just want to be able to see for every user, how much have they spent? And I'd be able to go through and say, maybe send an email to the people who have spent a lot. Okay, thanks for being a loyal customer. Versus people who haven't spent, I could go through and send an email like, here's a coupon for your first purchase, 10% off, something like that, right? Where I want to basically get some insight where it involves knowing everything about all users. And some of them have corresponding orders and some of them don't. Now that brings us to another topic, which is, okay, but we have nulls here. So is there a way to change that? Let's say I wanted to do the same thing that we had up here where we had our high spenders, right? So we selected and we summed all the orders based off of grouping them by customer ID. So it's a lot again, but let's do that here with a left join. And there's going to be a slight difference, right? Because we have nulls. So if we do this, select first name, last name, order date, and amount from customers, left join orders, and we do a group by customers.id this time. So that will group by customers so that we have these two grouped, on his own, on her own. And actually Blue is a girl. I'm sorry, Blue. Okay, so if we do this, we won't see much difference. Well, we will see a difference, but it's not very meaningful. What am I missing? Extra semicolon. Not that useful because it just condenses our data and hides stuff. But if we go through, and I'll format this again, let's sum together everything, right? So we'll sum, and inside of here, we want to sum amount. And we don't actually need to have amount there. And we can get rid of order date too. So let's just have the first, last name, and then sum. Okay, so this is accurate, that's accurate, that's accurate. We still have null here, which it can work. But it would be nice if instead it just said 0, because they've spent $0. So how do we do that? And this is not this is not a join specific thing in any way. This is just an interesting problem. How do we get, instead of null, how do I replace that with 0? And there's a couple ways. The first really lengthy, awful way is to use a case statement. So I could have a case statement where I checked, is some amount is null? Remember, I can't just say equals null. But if I said it's is null, then do 0. Otherwise, do some amount. But that's kind of long. So it's going to be much easier if I use what's known as if null. And I haven't shown this to you yet because we didn't really have many cases where we had null data. But here's one. So what if null does, it takes 2 arguments. The first one is the thing you want it to check if it is null or not. So we want to check, is sum of amount null? So here it's not, right? It's not null. It's not null. Here it is. So then the second argument is what we want to replace it with if it is null. And we'll just say 0. So it's very simple. It checks if the first argument is null. If it is, it replaces it with the second argument. If it's not, it leaves it as the first. So now if I try it, perfect, we get 0. We should definitely add an alias. Let's call it total spent again. Okay. One other thing that would be nice is to order by total spent. And this time, let's do it from least. So we'll just do order by total spent. And that should work. There we go. And now you can see we have 0. Okay. So we kind of talked about a lot. There's a couple topics that touch on each other. The first thing, just to recap, was that I wanted to show you when we do joins, any joins, they're not fancy special tables. They work just the same way as any other table. So we can do things like group by and order by. Then the next thing was that we saw inner joins. If I go back, we saw this. And then we also saw a left join. And the key difference, they both join data from two tables, but the key difference is what data they join. So we give them a condition, but even given the same condition, in our case, it was join on customer.id equals orders.customer.id, this middle part. And on inner join, that's all we get is the exact overlap. On a left join, we also get the left part in addition. So every customer in our case, which can be useful if we wanted to see things like which customers hadn't ordered things, which is what we got here. So hopefully that explanation made some sense. I totally understand if it didn't. This is a tough thing to really wrap your head around at first. Now, it's not terribly difficult once you get going with it, but understanding it can be super intimidating. So if you're in that situation, we will have exercises coming up in just one more video after this. And I recommend you try and go through those. And if that's not enough, then absolutely ask for help in the forums here. This is one of the crucial things that, in my experience, sometimes takes students a couple of maybe hours, a couple of days, not like 12, 20-hour days. I just mean sleeping on it once or twice to help kind of get some space in your brain. Anyways, hopefully you're able to kind of get where I'm going with this. Next up, we're going to see our last type of join, which is a right join. Very simple. Well, it's not simple, but very easy to grasp if you understand left joins. Okay, so we hopefully survived the last couple of videos on joins. We had cross join, the useless one. Then we have inner join and then left join. Now we have the sister or brother of left join, which is right join. So this should be a pretty short video. It's very similar to left join in that it takes everything from one column it takes everything from one table along with the intersection, along with wherever the join condition is met, but it just does it from the other table. So in this case, we've been doing customers and then orders. So if we did a right join, it will take every record from orders along with any matching records from table A, which is our customers. Now the thing is, and maybe you've thought about this already, we don't have any orders that don't have an existing customer. So we're actually not going to see a difference. But I'm going to come up with a way. I'll show you a way for us to see a difference. But to start, let me just show you the syntax. Okay, so let's hop over to Cloud9. And here's our simplest left join that we wrote. Remember, it does this here, where it includes everything from customers, David Bowie and Blue Steel included, even though they don't have any matching records. And then it also includes all matching records. But rather than that, I'm now going to go and retype it down here as a right join. So we'll do a select, and we'll just do star from customers, and then we'll do join orders on customers ID equals orders dot customer ID, just like that. However, if we leave it like this, remember, if we don't explicitly say what type of join, it's implied to be an inner join. So we can actually start with that because it will be good to see what that looks like and compare it to what we get when we do a right join. So when we did left, which was right here, we have these nulls. And we have, 1, 2, 3, 4, 5, 6, 7 entries. Versus when we do an inner join, we have 5. And if we make it a right join, all we have to do is change that. If I can type right, there we go. Let's try this one. And we have 5 again. 1, 2, 3, 4, 5. And actually it's identical to what we got when we did the inner join. And the reason that's happening, I kind of already went over this briefly, but the reason it's happening is that we don't have any orders that don't have a match with a customer. So everything we have, if we go back here, everything we have in the orders table has a matching customer. So there is something to join it on. So for every order, we actually have 5. This table only has 4, but we have 5 in our database. Then there's only going to be 5 joins or there's going to be 5 records that are joined when we do a right join. When we did a left, we had we had a couple of users who didn't have any records, who didn't have any orders. So these customers like David Bowie and Blue Steel didn't have a match, but we still included them. So how can we actually see something different? How can we tweak our data so that a right join actually results in something distinct? Well, there's a simple thing we can do, which is to screw with our data, to mess with our data. So that's what I'm going to do here. I don't necessarily recommend that you follow along exactly because I'm going to be messing up some of the data. I'll fix it towards the end of the video, but I don't want you to have to go through that process if you don't want to. So it's non-essential. What is essential is how the join will work, which we'll get to. So the way that we would have a difference, we'd have a unique result between right and inner, is if there's something that we have on the right table, which for us has been orders. In the orders table, if there's something in the orders table that doesn't have a match over on the left, that there's no join, so that would mean that there's no customer. And right now, it doesn't make sense, honestly, to have an order without a customer. But maybe, let's say, someone accidentally deleted stuff from our database. Or maybe there's a wrong ID, a wrong customer ID in our data. We would be able to spot that using a right join. So what I'm going to do is hop back to Cloud9, and before I do anything, I'm just going to rerun this early inner join we did. So as we can see, of course, on the left, we have customers. On the right, we have orders. And we have Boy George, who has 2. Let's say I were to delete Boy George, and then I ran an inner join. Well, these would be gone. And we would only have 3 customer orders, right? But if I did a right join, we would have order, and null over here. So it takes all orders, regardless as to whether they have a matching customer or not, and they'll fill in null if there isn't a customer, and then if there is, the appropriate information will be filled in, just like it was with left, except, the opposite direction. So let's try that. Let's try deleting a user or a customer. Let's delete Boy George. It's been a while, but that's going to be delete from customers. I keep calling it users. Where, and we could do it based off of ID. Let's do it based off of first name. First name equals boy. Just like that. Now, what do you think will happen? Oh no, an error. And you may have anticipated it being a syntax error based off of my typing proficiency, but it's not. It's a deeper error. It's an error that has to do with that foreign key constraint we set up. Because if we try and delete a customer that an order is referencing, we have 2 orders referencing it, that's a problem according to our foreign key constraint that we set up here. Remember that this doesn't let us create an order with a faulty or non-existent customer ID. So it also won't let us delete a customer up here if it's dependent on down here. And I kind of did this on purpose here to show you a solution to this. Not to let us delete things willy-nilly, but how could we, if we deleted a customer, how could we automatically have it delete all orders associated with it? Which is a pretty common thing. If you have data that's dependent on another piece of data, let's say we have books and reviews. Well, if that book is deleted for some reason, we don't want all these reviews that are just pointing to an empty or gone book. So we would want to link them. So if I delete the book, all associated reviews get deleted. And I'll show you how to do that. But the first thing I'm going to do is delete these two tables. I'm going to remake them. And this is the part I was saying you do not need to follow along. So let's do that now. Drop table. And we have another little surprise in store for us. If we try and drop table, and let's just do customers, what do you think will happen? Same issue. We can't delete customers because orders depends on it. So what we can do is delete orders first and then customers, or we can do it in one line like this, orders, comma, customers. Well, if I put an S there. And now, of course, I messed it up because orders is already gone. So if I had typed that correctly, it would have worked, but we'll just delete customers separately. Now, if I do show tables, there's nothing there. Okay, so the reason I did that is I want to remake our two tables very simply. So I'm going to copy this. And this is why I was saying you do not need to do this yourself necessarily. And I'm going to change one line. I'm going to get rid of the foreign key constraint, just like that. Everything else should work exactly the same. So I'm going to remake the customers table, remake the orders table. I'm going to insert our customers, and I'm going to insert our orders, just like this. Okay, so if we do a select star from customers, let's say, we have the same data, same thing from orders. But now what I'm going to do that I couldn't do before is I'm going to insert a new order. So insert into orders, and I'm going to insert, what do we have? Order date, amount, and customer ID. And I'll do two of them. And so the first one will be something ordered, let's say 2017/11/05. And the amount was $23.45. And the customer ID, this is the important part that I'm trying to highlight here. I'm going to put something in that doesn't exist in our table. So let's say 45. And I'll do one more. I'll do, rather than this, let's get a little practice. Remember using cur date, gives us the current date. Let's do that. So we'll do cur date here, comma, and this purchase was for 777.77. And that was made by someone with ID 109, which also doesn't exist. Perfect. So now let's insert those. Didn't seem to have any problems. Let's look at orders. Yeah, it's here, right? We have customer ID of 45 and 109. And the reason this works is we got rid of that foreign key constraint, which I'm not saying you should do, by the way. I'm doing this to illustrate and make a difference in our data. So let's suppose we're inheriting someone else's database and they decided not to use they didn't know about foreign key constraints, so they didn't use it. And then they had users, they used to have all the way up until 109 users or customers. And then a lot of people left. They just deleted their accounts. Let's say something bad happened. There was a hack, a data breach. Everyone got scared away. And then all we were left with are these customers. It's pretty sad. So it's a great bunch of customers to have, honestly, but still only 5 compared to 109. Keep in mind, this is all a dumb made up story. But what we could do is use a right join to basically identify all of our customer and orders and their associated orders, as well as any orders that don't have an associated customer. So we could fill in null. So if we do our join that we had done earlier, I'm just going to scroll up to save time. If we do this join here, which is an inner join, or that's actually a left join, let's do this one right here. Nothing changes, right? We still have Boy George and his associated 2 orders, George Michael, his 2 orders, Betty Davis, her 1 order. And then if I did a left join, which we could just do by simply changing that one inner to be left, or we can just do this here. And I'm only choosing this one because rather than star, this has a smaller subset of data that's easier to look at. Okay, So now we end up with this, which still is unchanged from when we did it in the last video, because there are orders that have no customers, but they're not here because we did a left join, and the left join takes everything from customers and any associated matching data from orders. But now, if we do the same thing down here, if you can hear my cat meowing, and we just change it to be right join. So we're still just doing first name, last name, order date, and amount from customers on the left, or from, on the left is the wrong term, but from customers first, right join with orders, so that we take everything from orders, like this, everything from orders, and any overlap from customers. Let's try it. And you can see exactly what we expected happened. So we still have all of our orders that match, customers and orders, but then we have those two orphans that we added in, where there is no matching customer. So we end up with null first name, null last name, null first name, null last name. So that's basically all I wanted to show you with right joins. But like I said, we will have actually relevant, useful examples later. But the last thing I wanted to do was hit you with a whole bunch of setup, brand new data, just so that we could see how a right join works. So there is, this is a hypothetical situation that could happen. We could have orphan data like this. So I'm going to show you two things now. The first one is that we can still just do anything that we want with this data like we did earlier. We can do more complex selections. And I'm also going to show you a new constraint you can add to your schema so that when something is deleted that has a foreign key depending on it, it will automatically delete the dependent record. But to start, I just wanted to show we can still do things like group by, or we can do things like order by. So we can add that in here. Let's do order by, and let's do first name, just like that. Okay. What about if we tried to group by? What if we did group by, and what if we tried to group by customer ID? What happens then? So it doesn't look like all that much, right? But we can still do our same, we have boy George was condensed, George Michael condensed, but we can do a sum for amount, just like we've been doing. And we can see how much everyone has spent. Boy George, 135, George Michael, 813, Betty Davis, 450. We still have these two nulls. So this is where we can start to make decisions and do things like, okay, if first name is null, then let's replace it with something. So I'm going to format this a bit as we start to get more and more. And we'll replace first name and last name with if null first name. And remember how this works. If first name is null, then it will be replaced with whatever we pass in. So we'll just say missing. And then we can do the same thing for last name. If null last name, comma, we'll say user. So we'll end up with missing user if we do it that way. If we don't have an error, or extra comma here, now we do it. And let's use aliases as first, as last. All right, got a lot going on. Okay, so now we have missing user. And let's say we want to see what the total of our orders are where we don't have a user. So basically the orphans, we want to group those together as well. Right now we're grouping by customer ID, but what if I wanted to group these two? What we could do is change customer ID to be first name, and we'd want to do comma last name rather than just first name because we may have multiple people with the same first name. So if we do this now, you'll see that we end up with missing user has 801 total spent, then Betty Davis, 450, and so on, and we could order it. I think by now you understand what I'm trying to show, that these tables aren't special. You just have to be comfortable working with null, and if null is kind of your best friend when you're doing that. Okay, so then the very last thing I wanted to show, I keep doing that, go away. The last thing I wanted to show was how we do what's known as on delete cascade. So this is what I was talking about. When we delete, if we have a foreign key relationship, when we delete a parent, so if we delete customers table, not the whole table, but let's say we delete Betty Davis, we want her order to also be deleted. So it's not just totally on its own. We don't end up with this situation. So how do we do that? Well, I'll show you right now. If you're not interested, then go ahead and skip. This isn't about joins, but I figured it's a good place to put it. I'm going to actually drop our tables again. I'm going to redo, so grab our original schema from way up here. Just copy, how much do we want? Down to here. And we still have our foreign key there. I'm going to indent this a bit. And all we do is add on delete cascade. And all that does is it says when a customer is deleted that has a corresponding order, delete the order as well. So let's try it. I'm going to copy this in. Let's make sure we don't have any tables right now. Perfect. So let's copy it. Then let's copy orders in. And then let's insert our data. And insert our data again. Okay, so as we know, we have data that is joined. I'm not going to spend time going over the joined part. Let's just do select star from customers. Okay, and then we'll do a select star from orders. And let's say we want to delete Boy George. Boy George has 2 orders, these first 2. So if I delete Boy George, these 2 should now disappear. Versus before, a couple minutes ago when we tried it, we had a problem. It's not really a problem, but we ran into trouble that we put in there ourselves because the foreign key constraint didn't allow us to delete it. We weren't allowed to delete a customer unless we deleted the order first. So we're going to do that now. Just try deleting based off of ID, or we could do it based off of first name. Let's do email. Okay, so we're going to delete from customers where email equals george@gmail.com. And we don't get that scary error. Now, if we look at all our customers, we're missing Boy George. And if we look at our orders, we're only down to 3. All right, now we're about to move on to our exercises. So you're going to get some practice on your own. Hopefully we have new data, so hopefully it's a little more interesting rather than having to work with the same old data over and over. And then we're going to keep moving on. All right. Okay, I'm back with a very quick addition. This is a frequently asked question that I get pretty often, which is there really a big difference between right and left joins if we just change the order of what we're joining? And the answer is no, they're actually the same. So if we do a left join, where this is customers A, and then on the right we have orders, that's identical to doing a right join if instead we put customers over here and we put orders under A. So think of it as just, flipping this. There's no difference. So let me show you an example. If we go grab our simple left join from way back here, this one right here, our simplest left join. And I will paste it down here just so you have it to see. And let's paste it in as well. Okay, first of all, there's a lot to look at, right? But what's most important is that we have on the left customers information first, and then on the right we have our order information, right? And then we have nulls where we don't have a matching order. Okay, so what happens if we try and do the same thing, but instead of doing customers first, we do orders, and we do a right join customers on customers.id equals orders.customerID. Okay, so if we do this, look at what we get here. So we have the exact same data, 1, 2, 3, 4, 5 rows, 1, 2, 3, 4, 5, but the order that they're printed is different, right? So we have on the left side now, we have our orders information, And then on the right, we have our customers' information. But the actual data that's displayed is the same. Yes, the order changes, but that's trivial. That doesn't matter. So in effect, these are equivalent. And in fact, some environments that I've come across, some development environments, won't even support a right join, and they just want you to do a left join and switch the order. So to sum up one more time, let's say I did the same thing here with orders and customers, but I did a left join. What would happen now? What's a left join with orders first and then customers? And the answer is it's the same as doing a right join, except if we start with customers and then orders. And unfortunately, we don't really have anything to see, right? Because our data doesn't have any discrepancies on the orders side. This is what the entire last video is about, which I will not retread here. But my point is that they look the same, and they look just like an inner join as well. But when we have something different, like with our left join for customers and orders, you can see that the data is actually the same. All right, so we made it through, or at least I made it through. Hopefully you're still hanging in there. Hopefully you're alive and you survived that section. I know it can be brutal. This is, for me and for most teachers, the hardest thing to teach. Not because it's technically that difficult, but it's a big thing. We have to have multiple tables, and to have multiple tables, we have to create the schema. We have to insert the data. Then we have to, show what the data looks like to understand it, and then we can get started with the joins. And you have to manipulate the data to change. It's just a lot of work, and it's tough. It's tough to keep it engaging. And frankly, I don't think that was terribly engaging. So I'm sorry. Hopefully you made it, and I'm doing my best to make the rest of these a little bit more exciting, because once we have these tools in our belt, it's a lot easier to start doing case studies, which we'll be doing, or making a full application. We're getting close to end products, to actually making things, rather than, silly one-off little examples. Okay, so it's a long preamble. It's now your turn. And this is where you'll probably, if you're confused, if you're stuck with this join stuff, this is hopefully where you'll be able to make some big connections, to have some breakthroughs. So this is a little different than exercises we've done in the past. There's only one schema, one table you'll be working with, and there's not even that many questions. But the first thing is that we're going to be working with students and papers. So I'm a teacher, let's suppose, I guess I am a teacher, but let's say I'm working in a classroom with high school students in an English class or a literature class. It's going to be very, very simple data. I'm telling you what I'm looking for. Students and papers. And for students, we'll only worry about an ID and their first name. So don't even care about a last name. We'll just make sure first name is unique. And then we're going to have papers. And it's a one-to-many relationship. One student can have multiple papers, but a paper can only belong to one student. So these papers will have a title, a grade, a letter grade, a numeric grade, like 90 or 60 if they don't do particularly well. And then a foreign key student ID, which is referencing the student ID. Okay, so that's the basic schema, and I'd like for you to first go through and actually implement this. And don't worry about the data, because on the next slide, I'm giving you the data. You can copy and paste it in. So this data is what we'll be working with. So we have 1, 2, 3, 4, 5 users, students, I keep doing that. And then we have 5 different papers. But there's a couple important things. One is that a couple of students actually have multiple papers. So for instance, if we take Caleb, his ID is 1, although you can't see that here, but he's the first one inserted. So his ID is 1, and he has my first book report, which didn't get a great grade, 60%, and my second book report, which only did marginally better, 75%. Then we have Samantha, who wrote Russian Lit Through the Ages, and we also have another paper by her, De Montaigne and the Art of the Essay. And then Raj, looks like we don't have anything from Raj, where his ID is 3. I don't see anyone or any paper with ID of 3. Then we have Carlos, who wrote Borges and Magical Realism. And then we have Lisa, who didn't submit anything either. So let's say, and the whole point of this is that it's the end of the year, and I'm trying to figure out who submitted what papers, what their average grades are. If I need to, talk to somebody about they didn't turn anything in, who's going to fail, and so on. So here's the data we're working with. But the first thing you need to do is write the schema. So just again to reiterate, primary key, foreign key. Varchar, varchar, integer, integer. Okay, moving on. Once you have that done and you have your data in, you can play around with it, but I'd like you to print this first table. So all that we have here is first the name of a student and their corresponding paper, the title and the grade. Samantha and her 2 papers, Carlos and his paper, Caleb and his 2 papers, and then the corresponding grades. So this is a join. What type of join is it? And you only need these 3 things. So I don't want to see ID, I don't want to see student ID, just first name, title, and grade. And then once you've done that, we have another join. I'll give you a hint. Everything in this section, in this exercise, involves a join. This one is different because we have the same basic stuff, Caleb and his 2 book reports, Samantha, her 2 papers. Raj, though, null title, null grade. Raj didn't have a paper. Carlos, Borges, and Magical Realism. And then Lisa, null, null. Lisa doesn't have a paper either. So print this out. It's a different join. Then once you've done that, move on. Similar, but notice instead of having null and null, when a student didn't turn any papers in, we now have missing and 0 for their grade. Missing for title, 0 for their grade. So it's the same thing here. We're just subbing in. Okay. Then we get to this. This is going to be an average grade next to every student. So we have Samantha, and the average of her 2 papers is 96. Carlos, the average of his 1 paper is 89. Caleb's average for 2 papers is 67.5. Raj has an average of 0 because he didn't turn a paper in. And Lisa has an average of 0 as well. So I won't give away too much about this, but you can use the same join you used here. You just then need to condense it. We need less information. You'll need to, I'll leave it at that. And then finally, print this. An extension of what this one was, except there's a new column, which is passing status. And passing status just says if the student is passing our class or not. And the threshold, I should have written this out. The threshold is if they get a 75 average in the class or higher. So Samantha passes, Carlos passes, Caleb unfortunately is below 75, so he fails, as do Raj and Lisa. All right, so there's a bunch of joins you need to write. First things first, though, get the data in there. Create the schema, get the data in, play around with it, and then attempt these, 5 joins? And I'm back here with a solution, or multiple solutions, to go over these join problems. So again, this was a one-to-many relationship, students and papers. And the first thing we're going to do is go over to Cloud9, and I'm just going to work in the same database, but I'm going to make a new file just because it's getting crazy. And I'll call this one studentspapers.sql. Okay, so we know we need to create 2 tables. Create table students, and I'm just going to leave it empty for now. And then create table papers. Also leave it empty. Great. So next, what do we put in them? So we'll start with students. Simple. It's an ID, but we said is a primary key, integer, which means it should also auto-increment, unless we want to do it manually, but we don't. And then first name is a varchar. So we have ID, int, auto increment, primary key. And then we have first name, which is just varchar, and we'll do 100. It's a good, even, nice number. So that's it for students. But then we have papers. So papers has a title, grade, and student ID. Let's start with just title, grade, student underscore ID. Perfect. And I'm noticing, I capitalize this. It doesn't really matter, but it's going to be annoying to remember that, so I'm just going to put it back as lowercase ID. So we've got title, grade, and student ID. Title is a varchar. We'll also do 100. grade is an int. And then we have student ID. And student ID is a foreign key referencing students.id. So it's just an integer, and this sometimes trips people up that we just write student ID int, and then the next line is foreign key. The field that is foreign key is student ID, this right here, and we need to say what it references. So it's referencing students table, the ID field. Okay, and we could also indent it like this, because this has to do with this. And then if we wanted to, which you did not need to do, but this is where we could add on delete cascade, which you may, and we saw in the last video or 2 videos ago, it's not necessary here, we're not deleting anything, but you could put that there. Okay, so the next step is now just to create them. So before I go too far, I did catch this, I have an extra semicolon there, get rid of that. But we'll create our students table, and we'll create our papers table. Everything looks good. And if we do show tables, I'm still working in our same database, so I have customers and orders, that's fine. But I have papers and students. Okay. And we haven't done this in a while. How about we describe students? Cool. So we now have auto increment in there, primary key, and that's for students. And what about papers? If we do describe papers, well, you can see we have title and grade, and then student ID. Okay, so next up is to get our data in there. And I said that you definitely didn't have to do this yourself. So I'm just going to put it in this file so you have a solution file. But it would be annoying to type this. I had to type it. I totally get it. So paste that in. Perfect. So now we can do a select star from students, and we should see our 5 students, and do a select star from papers, and we see our 5 papers with student IDs. Great. So the first thing to do was to print this join table where we have first name, title, and grade. Nothing else. First name, title, and grade. Where, and what's our join condition here? Well, basically where the student.id is equal to the student ID in the paper. And this we could accomplish through an inner join. That'd be the easiest way. We could also do it with a right join if you wanted to, which we'll take a look at, but an inner join is the simplest way. And I'm going to do an explicit inner join. So that means select, and let's start with star from, and let me put a number here, exercise 1. Select star from, I'll do it on a different line, from students, join papers on students.id equals papers.studentID. And let's be explicit with inner join, just like that. So if we take a look, you see we have the right data, right? We have Caleb and his 2 books, Samantha, or 2 reports, Samantha, her 2 essays, Carlos and his 1 essay, and we have the grades. Now we don't want ID and student ID. So we just need to get rid of that. And the simplest way is just to explicitly say what we want. So grade, title, and grade. Okay. Now we do it, and we're good to go. There's one thing, and this is my fault for not mentioning, in the instructions. I did order this, and totally fine if you didn't do it. If you did catch it, congratulations on looking at that. I didn't. I forgot. I did this late last night when I created these slides. I'm recording it the next morning. So this was ordered by grade. So that's simple too. Just going to be order by grade. And what order is it? Well, it's descending. Now we do it. And now we have the correct answer. The other one was correct too, I promise. The only thing that I'll address here is that I mentioned that you could also do a right join. And why is that? Well, let's just verify, see if I'm crazy. Nope, it still works. Phew, good to know. I'm just kidding. But the reason that it works is because if we go back to our slides way back, when we do an inner join here between students and papers, all of our papers have a student they belong to. So basically this section is the same as this entire section here, the same as this. If we pretend that left join doesn't exist, ignore that slide, this intersection is the same as this because every paper has a student ID in it. So you could also do a right join. Nothing wrong with that. But I think the inner join is easiest, although it's easiest because it's just, this is how I think about joins most of the time, but it's not any easier because it's just a single line or a single word that we're changing. Okay, so I'll just write alt solution. Okay, moving on. Print this. So very similar, right? Caleb, Samantha, their respective books, but then we have Raj and Lisa who didn't write any reports or any papers, and we have null in place. So this is a left join. And the way that we're going to do that, if we go back to our slides again, we're going to grab everything from students and then any associated papers, but some of them don't have papers, and those will then be filled in with null. So let's do this now. We'll call this, let's call this problem 2. And we'll start with select star again, and then we'll alter that from students. And then we need to do a left join. Papers on students.id equals papers.studentID. And we'll leave it at that to start. And you can see it's working. We've got Caleb and his stuff, Samantha, her essays, her papers, Raj, null, 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 Lisa, null, null, null. So we're getting every single student, Caleb, Samantha, Raj, Carlos, Lisa, and if they have a matching join condition in the papers table, then we also get their paper data. But if they don't, we have null. The only thing left is to whittle it down to first name, title, and grade. Just like that. Let's verify. Okay, and is there any sorting here? No. Then we're done. Okay, so problem 3. It's very similar, but we're going to then substitute in for null under title, we want it to say missing, and under grade, we want it to say 0. So we can actually just use the same thing, so it's going to be select. I'll do this on separate lines. First name, comma, title, comma, grade. From students, left join papers on students.id equals papers.studentID. Quite a mouthful. However, when we're working, so first name will be the same, but title, we're going to, if it's null, we're going to make it the text or the string missing. And that's where our lovely if null function comes into hand, or it's handy, let's say. So, comma, and we'll just replace it with missing. So remember, I'm beating a dead horse, hopefully at this point. If null takes this, if title is null, then it replaces it with missing. Otherwise, it just keeps it as my first book report, my second book report, and so on. So we'll start with that. You can see we get missing, but we still have null for grade, and that's a simple fix, the same thing. If null, grade, comma, and we want 0. Not text, not a string 0. We want the number because this is an int over here. Perfect. And we're done. We get missing 0, missing 0. And then things that didn't have null are untouched. All right, moving on. This one is similar in that we want to have data for students who don't have papers, so Raj and Lisa. So this is not going to be an inner join. We know that because if we did an inner join, we would only get these 3. We wouldn't have anything on Raj and Lisa, our students who maybe aren't doing so hot, they're not turning things in. But what we want is only the first name and their average for all their papers. And if they didn't turn anything in, their average is 0. So what this really means is we need to group. We need to group our students. And we're going to start by selecting all of this. And we'll get rid of our if nulls. So let's just do title again. And we don't even need title, do we? We just want grade. We'll start with that. So if we do a left join, okay, we get this. This is actually close, right? The only thing is we need to condense our data. We need to group these together. So what's the best way to group them? Well, we could use first name. That would absolutely work. They're unique. We could not use on the papers side of things. We could not do papers.studentID because Raj and Lisa don't have papers.studentID. So that's null for them, which is problematic. We can't really dependably group by null. And also, we don't want to group Raj and Lisa together. So we want to group from this side of the table. And we could do names, but there's also something else that we're not seeing. If we do star, we can just group by students.id, as you can see here. So what I was saying is that student ID doesn't work because these are null, and if we group, we don't want these together. We want them separate. So let's group by students. And we could get away with just saying ID because there is no ID on our papers table, right? We didn't have ID, which we probably should have just for good practice, but we don't have it. But if we did have it, then we definitely need to be explicit and say students.id, and it never hurts to do that. So we'll group by students.id. And if we copy it and we paste, okay, so we're getting close, sort of. We have things grouped, and remember that hides data from us because it's grouped behind this row. All 2 of Caleb's papers, 2 of Samantha's. But we're at least getting data grouped. So then the next thing is rather than displaying grade here, we don't care about grade. What we want to display is the average of all the grades for those 2. So Caleb has 2 grades, 60 and something else. Samantha has 2. Raj has, we'll have to deal with that in a little bit. Carlos has 1. Lisa has null. We'll deal with that in a second as well. But let's see what we get now. Okay, so we get 2 averages, 67.5, 96, and 89. 3 averages, excuse me. And then for our people who don't have papers, we end up with null and null. Simple solution. If they don't have any papers, we just use if null. If null, average grade, then we just want to make it 0. Just like that, before I deleted it. And now, you can see we get Raj and Lisa have 0s. And if we check against what we had here, there's only one small change, which is we need to order them. Descending order. Order by average. And actually, rather than doing average grade, let's just give this an alias, which is what I did over here. I just called it average. Now we can do order by average. Perfect. And there we go. Well, nope, I lied. Order by average descending. And now there we go. Okay, perfect. Moving on. Our final problem. Same thing, although we're just now adding a passing status. So a new field that doesn't exist in either table. And that says passing if the average grade is greater than 75 or equal to 75, and failing if it's less. So this is a great use for a case statement. Okay, so let's give it a shot. This one is very similar to the previous problem, so I'm just going to copy it, paste it, and just rename it problem 5. So all we need to do is add in another field, but this field involves a case statement. So what I like to do is always do my case and end together. Case end, and we'll call this passing status? There we go. Okay, so what do we fill in here? We're basically trying to say when average of grade, so we'll copy that, is greater or equal to 75, then what do we want? We want it to be passing. Perfect. Otherwise, we want it to be failing. And let's see what happens. Okay, so it seems to be working. Passing, passing, failing, failing, failing. One thing to note, though, is that when we're doing average grade here, for some of them, it's null. Remember that. And so it's important to realize if we work with null, is null greater than or equal to 75? And the answer is null, which is bizarre, right? Versus if we had done is 65 greater than or equal to 75, we get 0 or 1, true or false, but we're getting null when you work with null. Fortunately, that is working to our advantage because when we get null here, it basically the case statement moves past it, ignores it, and does the else. But it is important to understand that. So you could do something like this if you wanted to be extra careful. When average grade is null, then failing. So that would catch null right away. Then we have, okay, when it's a number greater than 75, equal or greater than 75, then passing. Otherwise, that means it's a number that's less than 75, and that means failing. So we won't see a change in our results here, right? It looks exactly the same. Passing, passing, failing, failing, failing. Passing, passing, failing, failing, failing. The difference is that we're not relying on this weird comparison between null, because it is bizarre. Is null greater than or equal to 1? And it tells us null. It just is useless. Null is a weird special value. It has things like is null. So let's take advantage of that just to be safe. All right, now we're done. Hopefully you enjoyed some of that. It's a little bit different than some of the exercises we've done in the past. Involves joins, but hopefully it's not too scary. And if it is, I'm sorry. I'm sorry. Hang in there. Okay, we're at the final video here, the final challenge, and this is the one that puts everything together. Or really, more what it's doing is putting together all 3 tables that we have. So what we're actually getting out of it is not that impressive, right? We're not doing any crazy analytics or anything like the previous one. Not that that was too crazy, but nothing like that. All that we're doing is putting the title of a movie or of a series, and then every rating that it got along with the reviewer who wrote that rating. So we've done the first part up until here, right, where we've done title and rating together, or where we've done reviewer and rating together. But now we're going to put them all together so that this is the information for one review, right? It's the movie that was, or the series that was reviewed. It was the person who reviewed it. Notice that we can cat them into one reviewer instead of first name and last name, but that's secondary at the end. So we have the series title, the reviewer's name, and then the rating they gave it. So we're basically just trying to take, let's do it here, take this and fill in the blanks. So instead of series ID, we're going to get the name of the series. Instead of the reviewer ID, we're going to get the name of the reviewer. Okay, so let's go ahead and start over here with our handy dandy comment. And we are on, what is this, 7? 6? Yes, 7. 3 tables. Okay, so we can start off with any of the tables. We're going to join them all together, but I'll start with reviewers. So we'll select star from reviewers, just like that, except I need from. Boring, we've done this before, blah, 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 blah. So the first step is to join it with the reviews table. So we'll have reviewers along with their reviews, along with the series associated with that review. And we're not going to worry about, people who haven't written reviews. That's fine. We're ignoring that. Okay. So to do this, let's start off, first of all, by joining it with join reviews on reviewers.id equals reviews dot, and then we need reviewer ID. So fun to write. And we do that, and we see things like, okay, Thomas Stoneman gave an 8.0 to some movie or some series with ID of 1. He also gave an 8.1 to whatever has ID 2, and so on. So we're getting close-ish. Now what we need to do is also throw on the series data over here. And the first thing I'll do is just make this explicit. It's an inner join. So we're going to do another join, and it's really easy. At least syntactically, it's easy. We just write inner join again. So what are we joining on this time? Well, we're now going to join on the only thing that's left, which is series. So we took reviewers and reviews, sandwiched them together where they intersect. Now what we're going to do is join a series where the series ID is equal to series ID here inside of the reviews. So let's do inner join series on series.id equals reviews.series underscore ID. Such a nightmare trying to speak all this out loud. But let's step through this. Okay, so we have sort of this middle table, let's say, which is right here. We have ID, rating, and series ID, and reviewer ID for our review. That's every review has that. And what we started off was joining it with the relevant reviewers. Now we're going to also take the series ID and find all matching series and stick them over here. And it's going to be a messy table. It's going to get all collapsed and screwed up. So let's filter out some things. So let's only work with the title, the rating, first name, and last name. Okay, so we're getting close now. So we're pretty much there. We have all of the data together. So we have Archer has an 8.0 rating from Thomas Stoneman. Thomas Stoneman also gave Arrested Development an 8.1, and he gave Bob's Burgers a 7.0. And then we can see, okay, we have Archer again down here from Wyatt Skaggs, who gave it a 7.5. So we have all of our data synthesized in one table. Now what we need to do is concatenate things together over here. So that's just simple. All we need to do is, instead of doing first name and last name, we'll do a concat first name, comma, space last name as reviewer, I think is what we called it. Yep. Okay, and then there's only one thing that we need to change other than that, which is right now, things are ordered by reviewer. Let's order them by title, which is what we did over here. So that's just a simple order by title. Now we should be done if I get rid of that extra semicolon. And here we go. So we have Archer, all of the ratings for Archer and the people who wrote them. Arrested Development, all the ratings and people who wrote them. And all the way down through all of our series that have reviews. So that's important. So only where we have reviews. So to summarize, let's go all the way back here. What we just did was basically take the reviewers table, smash it with the reviews table where they match. It's an inner join where's the overlap, right? So we take the overlap between them based off of ID here and reviewer ID. Then we have that second table that we then joined with series, where the series ID matched the ID of a series. So it's a three-way, two join statements, but three tables together. And that's why I decided to do many-to-many relationships after the simpler one-to-many. But hopefully it's not too intimidating. We did a bunch of exercises with them. You're probably a bit burnt out. I know I am from recording all of them. So I definitely recommend that you take a break. Before we move on, we're going to continue, of course, with joins and relationships, but we're only building from here on out. So congrats on making it through this part. Okay, so next up, we have a return to these long, annoying tables with quite a few fields on this one. This is sort of like analytics for our reviewers. And what we're doing here is compiling statistics on them. So Thomas Stoneman, how many reviews has he written? 5. Okay. What's the minimum he's assigned? 7.0. The maximum review is a 9.5. His average is 8.02. And then a status, which is saying that he is active. And that's determined based off if the user has any reviews. So Marlon Crawford has 0. So he is inactive, but everyone else is active. So we've got a lot of pieces here. And probably the most crucial thing to point out is that we have Marlon Crawford, who has 0 reviews, which we need to pay attention to we have to pay special attention to that because there's not going to be a natural join if we do an inner join. So we'll need to do a left join, which will highlight the fact that he has no reviews. And then the rest is not too difficult. Count, min, max, average, should be pretty comfortable with that. Status, we need to do some logic there. So let's start by adding in challenge 6. We'll just call this reviewer stats. Okay, so the tables we're working with, we've got the reviewer table, which is where we're pulling things like the name. And then we've got the reviews table, which is where we're pulling count, min, well, it's where we're pulling the actual ratings themselves. And then we're basically getting this data from there. So we don't need to worry about the series table. We're not working with that. We will be in the next, the final challenge here. We're going to put all 3 together, but in this case, we're not. So we'll start with a select star. Or let's just do, well, we'll do star to start. Select star from reviewers. We get all of our reviewers here. Perfect. We want all of them. So that will be the left part of our join. If we remember the 2 circles, A and B, this will be circle A right here. We want all of this to show up, even though Marlon doesn't have any reviews. Then we're going to do a join. Join reviews on reviewers.id. So where the reviewer ID, like this, 1, 2, 3, 4, 5, 6, is equal to the reviews.reviewer ID. And then in the case of Marlon, there is no reviewer ID equal to 7 in the reviews table. So we'll get null, 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 and so on. Okay, let's try it. And if we take a look at the results here, we don't get those nulls, and that's because we didn't specify that it's a left join. We left that off. And now, at the end, we have Marlon, Crawford, null, 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 which we'll need to make use of to do things like this, where we have 0, min, max, average are all 0, and then inactive. So we'll have to kind of make special exceptions for Marlon, or for anybody with null. Okay, so now let's start whittling down what we need. We want first name. We want last name. So what we have here, right? Then we want things like count, min, max, and average, which require us to group by. But let's start by just putting rating here without grouping and just verify what we need exactly. Okay, so here's all the reviews. And we want to group them together. And we could group based off of first name and last name, but that's not guaranteed to be unique, of course. So it's better to group based off of the reviewer's ID. So we can do that now. Group by reviewers.id, just like that. And if we do that, whoops, didn't mean to expand that. Again, our group by is working its weird magic. It's working behind the scenes. So now we can do things like average, for instance. Let's start there. Well, actually, even easier is counts. And we'll just count the ratings. So behind the scenes, it's grouped them. Remember, it went from this here. So if we take a look at like these, they were all grouped together. So under Thomas Stoneman, there's 1, 2, 3, 4, 5. But we only see Thomas Stoneman. We don't get 5 results, but they're there behind the scenes. So we'll do count rating. And you can see it looks good. We get 5, 9. You can see Domingo and Colt have written a ton of reviews, and poor Marlon just hasn't written any. So that's a start. Then we've got min and max. So those are quite simple too. Just let's start with min, the min rating that they've written. And that works for everybody except for good old Marlon, causing us problems. And we should be relatively comfortable with fixing this at this point. Notice that I just sent it to be 0. You could have set it to be anything. You could leave it as null, but let's make it 0 to match the chart. So we can use our if null min rating, then we'll set it to be 0. And if I leave it like this, our table is going to be kind of ugly because we have this if null up here. We don't need all this space. So let's call this one as count and this one as min. That should cut down on the space. Looking better. And then the same thing for max, which we can just copy and just change min to max. Okay. So we got min and max. Let's just triple check. There we go. Count, min, max. Then we've got average, which by now you should be comfortable with doing as well. It's the same thing as average, but we'll run into that same problem with null. We don't want null there. We just want 0. So if null, once again, just like that. We'll copy it. Okay. And we've got the first, almost everything, except now we need to work with status. And status is a little different because there's some logic here. And what's it based off of? Well, it's based off of count. So if count is more than 1, or greater than or equal to 1, then we'll call that user active, or the reviewer active. Otherwise, it's inactive. Or we could switch it around. We could say if count is equal to exactly 0, then status is inactive. Otherwise, they're active. And to do it, we could use a case statement. We can start with that. What we're working with, again, is count. So let's do this at the bottom, our case. And I like to do end as, and we'll call this status. Okay. And our first thing we'll check for in case is when count rating, and we can do when it's greater than or equal to 1. Then we'll say active. Status will be active. Else, and we need then here. Otherwise, inactive. Active, inactive. Okay, let's try that. Okay, it works just fine. But I did say there's another thing that we can do, which I also haven't shown you until now. I didn't want to overload you with a bunch of different ways of doing logic, but for simpler case statements, we can use another function, or another logical function, which is called if. So I'm just going to replace this with if. I'll show you what it looks like. We just say if, and then the condition that we're looking for. So if count rating is greater than or equal to 1, then the second argument is what we want to spit out. And then the third one is the else condition, or the else argument. So these are equivalent right here, as long as I put status. So let me make that a little bit easier to see. This right here is saying, okay, if count rating, so if the count of all the ratings per each user or each reviewer is greater than or equal to 1, then status is active. If that's not true, status is inactive. So this works great when we only have these two things that we're working with, right? Active and inactive. But if we wanted to add another thing in, it's a little more complex. Like if we wanted to say, okay, if it's greater than 1, then they're active. And if it's greater than 10 or greater than equal to 10, they're a power user or something. Otherwise, they're inactive. It's much easier to use a case statement for that. So I can show you that, but I'm going to get rid of this first and just make sure that our new addition works the same way. Looks good to me. We could go through and round. Average is kind of gross. But if we do that, that's going to get quite gross too. And we'll want to break that onto separate lines. We'd want to format that to make it a lot more legible. But otherwise, it looks good. So the last thing I'll do is optional. It's just to show you if we wanted to add in a third status from active, inactive, and crazy active or something like that, we can replace this if. Go back to our case. So we'll do case end as status, and we'll just do case when count rating is greater than or equal to 1. And actually, let's start with if it's greater than or equal to 10. In that case, we'll say power user. And then the next thing is when count is greater than or equal to 0. We'll just say active, else, and I need my thens. I always forget those. else inactive. So the way I formatted that is basically to say so the way that I formatted that is to say first, okay, is it greater than or equal to 10? Then it's a power user and we're done. But if it's not, that means that it's less than 10. So if it's less than 10, but still greater than or equal to 0, then they're active, and that should actually be greater than 0, not equal. And then if it's not greater than 0 and not greater than or equal to 10, that means they're inactive. So now copy that, paste it over, and you can see we have 2 power users, Domingo and Colt, who have count of 10. And now we're done. So we made it through that quite a bit there. I will leave this example, but I will also duplicate it and go back to having that simple if statement so we don't have to have the case. Okay, so I'll do that. You don't have to watch that, but it's in the solution text or the solution file if you want to take a look. Okay, so next up we have another nice clean table, just 3 results. And as you can see, what we're doing here is grabbing things based off of genre. So we only have 3, fortunately: animation, comedy, and drama. And then what we're doing is computing the average review or the average rating for each of those genres. So this will be a little similar to what we've already done earlier in this problem set. The main difference is that we're working with genre now rather than just the title of a given series. Okay, one thing I need to correct the record here. I called this challenge 5. I was wrong. After 3 comes 4. Now we're on challenge 5. Okay. And we'll just call this genre average ratings. Okay, so to get this information from our 3 tables, the 2 that we need to identify that we're working with are the series table, because that's where our genre information is stored, and then the reviews table. That's where our ratings information is stored. So we don't care about the reviewers, the people who reviewed them. That doesn't matter. All we need is the genres and then the ratings. So we can start with either one. Let's start with star from series, just like that. Okay. So all we're going to want to work with is the genre portion, but we're going to need to join with the reviews table. So we'll just do that now. Select star from series, join reviews. Hopefully this seems familiar now. On series dot id equals reviews dot series id. And if we leave the star in there, we're going to get a lot of stuff. So we don't need all of that. Let's just pick out a few things like title, genre, and rating. Okay, so now we can see we've got, all the ratings for Archer, all animation, of course, because they're the same exact row here with a relevant rating appended. So we've joined them together. It's an inner join, and that's what we want. We don't want to be working with, non-existent ratings. We don't want to take, let's say, Pushing Daisies, which didn't have any reviews. Well, that's a comedy, I believe. Maybe it's a drama, I don't remember. But whatever it is, we don't want to try and average null into the average rating for dramas or the average rating for comedy. So we don't want to do a left join. We want inner. Okay, so we've got this on series ID, blah, 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 blah. Now all we need to do is group things by genre. That's what we're trying to do here. Rather than by title, group by genre. And if we do that, we should see this is immediately reduced down to 3 rows, although remember that it's just kind of hiding all the data that lies beneath. So we have animation here, but it doesn't mean that there's only one. It's just that group by, when you use a group by, it's displayed in a very weird, awkward way that I think is kind of confusing. But what we want to do is we can get rid of the title too, rather than just genre and rating, we just want average rating. And that should do it for us. And we get the average ratings. And there's an alias, so you can add that in like that. And that's it. So now we get animation is the lowest rated, still quite high. Comedy is the highest rated, 8.1. and drama is right in the middle, 8.0. And I suppose this is as good a time as any to introduce the round function. We haven't used it yet, but we're getting a lot of decimals here, and we don't care about them. Let's just round it to, let's do 2 decimal places. So it looks like this, round, and I'll do it on separate lines here. So we have round average rating, but we don't just say round average rating, we have to supply what we want to round it to, 2 digits for us. And then we'll use adds average rating. So I could have done it all in one line, a gigantic, gross line in my opinion. So it's a little better to break it up like this. Takes up more space, but it's the price we pay. Okay, so round the average 2 digits and call it average rating. Now let's double check that works. And there we go. Much easier. You didn't have to do that, of course, but I figured it was a good thing to show. Okay, moving on to our next challenge with the same data, something a little new and frankly refreshing to see such a short table. So what we're doing here is identifying the unreviewed series in our database. So there are a couple that nobody has written reviews for whatever reason. I haven't seen either of these shows really. I've seen Malcolm in the Middle maybe once or twice as a kid, but I don't feel like I can review it, and apparently nobody else in our app felt that way. So we have 2 unreviewed shows. And the point is not to cheat and to just, use this information to find it, but to actually find it based off of the data we have in our database dynamically. So how do we write? It's going to be a join. What type of join do we need to write where we can see what series have not been reviewed? Okay, well, let's give it a shot. We'll hop over to Cloud9, and we'll start with our handy dandy comments. We are on challenge 5, and this one is unreviewed series. Okay. So what tables are we going to need to join here? So we've got, if we go all the way back here, we've got reviewers, we've got series and reviews. And we don't need to care about reviewers. We don't care about names of who is reviewing things. What we care about is the overlap or lack of overlap between series, TV shows, and reviews. So let's start with a simple join. Select, and we'll do star from series. And we can just start with that, nice and simple. It doesn't tell us anything. We have no idea which ones have been reviewed or not. So we need to join it with the reviews. So that's going to be join reviews on, and this is going to be our typical join. So series dot ID equals reviews dot series ID. And let's make this explicitly inner just so we're clear there. And when we do this, we get a lot, right? We see Archer with an ID of 1 has been reviewed with 8.0, 7.5, 8.5, 7.7. But there's a problem here, which is it's not doing what we want. We're not really close to what we want. In fact, we're ignoring the data we want because this is an inner join. So this is only finding the exact intersection between reviews and series. So wherever they overlap is what we're seeing. But we also want to identify where they don't overlap because that tells us that there's not a review for a series. So what we want to use is a left join. So hopefully that makes sense why. Because on the left, if we have our series, right, we have all the series, some of which have matches, some of which don't, and we do a left join, it's going to take everything from the left, including the ones that have no reviews, and it's still going to stick them in the join table, but it's just going to fill their values with null. So we'll be able to identify that. So if we change it to left join, and we scroll through some of this, you'll see somewhere, so we've got Archer with all these reviews over here. If we keep going down, here we go. Malcolm in the Middle has null, 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 because there are no reviews to match it with. But because we did a left join, we still get Malcolm in the Middle and Pushing Daisies, which is also, Pushing Daisies, which is null, 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 null as well. So we can use that to our advantage, because wherever we see null, means that there are no reviews. So what we want to do first, let's whittle it down a little bit. What we're looking for at the end is just title, but let's start by just doing title and rating. Let's do that. So it's a little easier to see. Okay, so now what we want to do is only work with the data where there is no rating. So that's actually quite simple. All we need to do is use a where, and then we can pick rating, for example, equals, and we can't say equals null because that's problematic. Remember, what we need to do is null, just like that. So let's try this now, and you'll see we only end up with these two, title and rating. And we don't have to do rating, by the way, because there are other fields that are null. If we go back to star, there are quite a few things that are null. We could have done ID, although this is reviews.id. We could have done rating, series ID, or review ID, or reviewer ID, but it doesn't matter which one we pick in this case. So let's go back, and all we actually want to do is select the title. That's all we need here. Paste that in. Okay. Only thing that's missing is the alias. So we'll do select title as unreviewed series. Copy that in, and it works. Okay, so the key thing here was that we used a left join. We wanted to highlight those discrepancies. This is a use case for a left join where you want to see where there isn't overlap. So hopefully that helps illustrate a bit more the difference between inner and left joins. Because if we had only done an inner join here, we wouldn't get the result we want. We wouldn't have any nulls. So this wouldn't select anything at all. All right, moving on from the title and average rating challenge, we now have something new. For the first time, we're working with reviewers. So what we have here is the first name of a reviewer, the last name, and then their rating. So for every single rating that's been given, we want to have the rating, or for every review that's been given, we want the rating and then the first and last name of the reviewer who gave that rating. So it's pretty similar to what we did up here with movies and ratings or series and ratings, except now we're working with the other table. So if we have these three tables, right, we've worked with, let's go back here. We've worked with series and reviews together. Now we're working with reviewers and reviews. So the outer two. So let's get started on this one. We will pop over here and just write challenge 3, obviously the most important part of this entire video. So we know we want to work with, let's start with reviewers. That's the first thing we want to work with. Let's take a look at those 7 reviewers. Okay, so for every review that these reviewers have written, we want to see the corresponding rating. And another side note, I deliberately put in a reviewer who hasn't written any reviews. We'll get to him or her in a little bit, but we don't care about that one in this case. So for this problem, we don't need to worry about that. Okay, so we've got select star from reviewers, and then let's just do a select star from reviews. And all we want to do is take these reviewer IDs, let's take 3 for Kimbra, and find all the matches where reviewer ID is 3. So here's one, here's one, here's one. As you can see, Cloud9 is actually highlighting them for me, which is really nice. So we want to join on this right here. So we want to join between reviewers and reviews where reviewer.id is equal to reviews.reviewer ID. It's a lot of review. Saying that over and over is a bit of a tongue twister. So select star from reviewers, and we'll do a join reviews on, and we want to do reviewer.id equals reviews.reviewer ID. It's a mouthful, but hopefully it makes some sense. You're starting to identify the patterns behind these joins. We've been doing these couple of times now between the last section and this section. So we're joining the two tables where reviewer ID is the same as, or reviewer.id is the same as reviews.reviewer ID. And what do you know? Did the same thing without the S that I just warned you about. Okay, so now, once we fix that, we have a giant list for every review that's been made. Over here, we have the corresponding first, last name, and ID of the reviewer. Now, this is more information than we needed to get because all we asked for was first name, last name, and rating. So let's now whittle that down. So rather than star, we'll select first name, last name, and rating, just like that. And now we get the right result. So I have a quick question, which is, what type of join is this? When we leave off the inner, it's still implied. So it's an inner join, the intersection of those two circles, the two tables. And so because it's an inner join, the order doesn't actually matter. So just to prove that to you, first, here's what we had before, what you expect. Now let's do the same thing, but let's select from reviews and inner join reviewers. Okay, so if we leave this at star, which is what we had before, you can see that the order that our data is actually kind of printed in the basic sense when we use star is different, right? We have on the left the reviews and then the reviewers on the right. But when we're hand picking things that we want, like first name, last name, and rating, it doesn't matter because we're dictating the order. I'm saying I want first name, then last name, then rating. So as long as the data is in the right place, which both of these do, they're combining them, whether we're doing reviews, inner join reviewers, or reviewers, inner join reviews, the same data is there. And then all we're doing is cherry picking what we want. So both of these work just fine. Okay, moving on to our next little challenge here. So here's what the end result should look like. We have two fields, just like we did in the previous one, but there's quite a bit of difference. If you notice, we have title still, so that's the same, but we only have one entry per series. So we don't have, Archer, 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 Archer. We just have Archer once somewhere. Where are you? Over here. But we also have average rating. So this is for all the reviews, all the ratings for a given title. Put them all together and find the average. And then the other thing is that the results are then ordered from lowest, average to highest. So basically, we're going to work with very similar data, take the same approach, join the same two tables. We're joining series with reviews. But then we're going to group them together. And then we're going to average the rating. And then we're going to order by average rating. And just like the previous problem, there are certain series that don't have reviews. They are not showing up here. So we don't need to worry about that. If we're worrying about nulls or non-existent data, that's not a problem for this particular challenge. So we're going to call this challenge 2, average rating. So if we just actually type a very similar thing, so select title and rating from series, join reviews on series.id equals reviews.seriesID. This is going to get us really close. We have all the data we need right here. This is it. We don't need IDs or we don't need to worry about release years or genres or anything. This is all we need. However, we need to group things together so that all Archer reviews are together, all Arrested Development reviews are together, and so on. So then that begs the question, how do we group them? What's the best way? And there's a couple of approaches that really we could do it based off of the name, the title, but that assumes that there's only one show named Archer, one show named Bob's Burgers, which is probably true 99.9% of the time, but it's possible that we have shows with the same name, or maybe there's a remake of a show. I'm trying to think of, I know there's been examples of this, where there is an older show that's been remade more recently, but basically it's best to not have to worry about that because we're not enforcing that the name of the show is unique. If we go to series, the only thing that has to be unique is ID. So it's much better to group based off of that ID. And of course it's here. Well, we're not seeing it printed out, but we can easily see it if we just add in series.id. So now if we run this, you can see we have that ID there. So even if we had another show named Archer down at the bottom with ID of 15, if we group by the series ID, then they'll be unique and they won't muddy the averages. They won't muddy the group by. So that should work fine. And we don't actually need that series ID anymore, but we're going to do a group by, and we need to do series.id. That's important. If we just do ID, that is confusing because it could also be reviews.id. Just to showcase that, if we just select star, and I'll get rid of the group by. If we just select star, you can see, even though it's still messy, we've got one ID here and we've got another ID here. So this is the series ID and this here is the reviews ID. So we need to be explicit. Okay, so let's undo our changes. Go back to what we had. We're going to group by series.id. And if we just do that, it doesn't get us that far. It gets us closer, but rating is just going to be basically the first one. Luck of the draw, essentially, it's not an average. It's just showing us one rating. Even though they're grouped by this ID here, we're still not getting the average. And that's a very simple thing to change. We just need to do average here, which we should be comfortable with by now. And let's give it an alias, average rating, just like that. Okay, let's take a look. Looking good. We've got title and average rating. A couple things. One, we need to get rid of ID. And two, we need to change the order. So let's start with a simple one, get rid of the ID. Then let's go ahead and at the end add an order by. So how do we want to order them? Well, what about just using average rating? So order by average rating, and then what order do we want? We can work with the default ascending order because that's what I have here, from 5.38 up to 9.9. And there we go, 5.38 up to 9.9. Now, that's basically the end, but I do want to highlight that these reviews are a little bit accurate, in my opinion at least. General Hospital, not my favorite show. It only gets 5.3 on average, probably well-deserved. I'm sorry if that's a show close to your heart. But I want to highlight amazing show that nobody watches called Halt and Catch Fire. I mean, look at this, it has a 9.9. How did that even happen? I mean, who decided that? That's real data coming from real people, millions of ratings, and the average is 9.9. Fantastic. Okay, but really, this is a great show. Nobody watches it. I highly encourage you to watch it, especially if you have any interest in computers, the history of computers, history of the internet. Although I will say season 1 is a little slow, but hang in there if you do want to watch it. All right, so we're moving on to our next problem in the next video. Watch Halt and Catch Fire. All right, so we inserted all of our data. We have our schema ready and all of our tables created. Now, let's get down to business. Let's do some stuff with it. So I'm going to break every problem that I'm going to give you, and there's quite a few here, into its own video. Hopefully it'll make them a bit more manageable and you won't want to go to sleep or drown yourself after watching it. So the first thing that you'll see here, the format of these is that I'm going to give you the results. It's much easier just to give you a picture of them rather than trying to describe in a bunch of text what it actually means. It's much easier just to show you. So first thing I should say is that these results are truncated. These are only for the first 15 or so. I used a limit, but I want results for everything. It's just too hard to fit them onto the screen. They would be very, very tiny. But the key thing is that we have title for a movie, for a series, and a corresponding rating. So we're going to need to join those tables together. We need to join the series table with the reviews table because right now they're not in the same table. We're storing the titles separately from the ratings. So let's do this now. We'll go over to Cloud9. And the first thing we'll do is just start simple. We'll select star. And we'll just start from series, which we've already done. Just like this. One thing I should highlight before we go too far, I did deliberately add some series that don't have any reviews so that nobody has rated them yet. And that was deliberate so that we can work with that later. However, in this example, I only want to see movies, I keep saying that, I only want to see titles of series that have been rated. So we don't have any nulls in here, which is a bit of a hint. So select star from series, and on its own we get this. Now what we want to do is join. So if we do a separate select star from reviews, we want to join basically where this ID of the series is the same as the series ID. So these first, let's see, 5 here, 1, 2, 3, 4, 5, correspond to Archer, which is what we see here. So to do that, we don't need 2 separate selects. We want to do select star from series. We'll do join with reviews on, and where do we want? We want to join on series dot ID equal to reviews dot series underscore ID. Just to reiterate, where this ID of the series, actually it's going to be easier if I do it here, where this series ID is equal to this ID of the series table. Okay. And all we want are title and rating, but we'll start with just getting everything. And let's see if we're in business yet. Well, it's a little hard to tell because we have this formatting issue where we have so much data, things are being cascaded over. But if we look closely, we can see, okay, we have Archer 8.0, Archer 7.5, Archer 8.5, and so on. And if we scroll down, you can see that not every single TV show is here. Like you'll notice the IDs jump. 7, 8, 9, General Hospital, 10, Halt and Catch Fire, and then goes up to 13. So whatever 11 and 12 are, we don't have any reviews. So that's good. Not that we don't have reviews, that's not good, but they're not showing up, which is what we want. So now we'll just whittle this down to title and rating, and that's all we want. And I'll format it a little bit nicer. Here we go. Hit enter. And now we get all of our data. On the left side, we have title. On the right side, we have corresponding ratings. So hopefully what we just did there seemed relatively similar to what we did in the last section where we were writing these joins. What we'll build up to in this section is doing a double join where we have another join statement because we want to connect all 3 of our tables. But for now, we're working with 1 table or 2 tables at a time. Okay, so we're done with that one. Let me just put a comment up here. First, let me just do challenge 1. And now we'll move on. Next video, we'll pick up with challenge 2. All right, so let's hop over to Cloud 9. And we'll start simple. Let's work with the reviewers table. It's the simplest one. So we're going to implement that first. So we'll go over here. And just to be totally transparent, I created a new database just so we have a fresh place to work. You don't have to do that as long as you don't already have tables named series, reviewers, and reviews. If you do, you may want to make a new database. So I'm working in one called something ridiculous and stupid that I probably will regret. TV review app. Yeah, not too bad. So we're going to start off by creating a table, which we're going to call reviewers. I swear to God, Blue. Stop. Calm down. So we'll start off by creating our table, which we'll call reviewers. And reviewers only has 3 things: ID, first name, and last name. So we'll start off with ID, then first name, and last name. And we know ID needs to be an int. This should be familiar by now. Auto increment, primary key. First name will just be varchar 100, and same thing for last name. So pretty straightforward table to start with for reviewers. The next thing that we'll move on to, before we insert things, let's actually get our tables going. So all tables first, and then we'll insert our data. So next up, we'll do series, ID, title, release year, and genre. So create table series, and inside here, we'll have an ID, which will be exactly the same, auto increment primary key. And these primary keys are especially important because we're going to use them as foreign keys in the reviews table, and we need to have valid rows that we're pointing back to. So we need to make sure whatever the series ID is here, that it's actually a series in our database. It's not pointing to some non-existent show or non-existent reviewer in the case of reviewer ID. Okay, so the next thing is the title of the series, which we'll just make a varchar. And then once we do that, we'll move on to release date, or released year in our case. And we have a couple of options for the data type here. So we could make it a date, but all we want is the year. And a date has this kind of format where we have the year, and then the months, and then, and so on, which we don't care about. So we could make it an int, and that would work, but then potentially someone could accidentally insert something with a release year of like 10,000 or 9999999, which is not a valid year. So there's actually another data type that we can work with, which I haven't shown you. It's just called year. And if we do year 4, it will be a 4-digit year, like 1999 or 2004. There used to be a year 2 type, but I believe it's been deprecated now. So we'll work with year 4. That's not the point of this lecture, so don't let that hang you up. I just wanted to show you that it exists. So we have that. And then the next thing that we have is genre. And genre will just be a varchar as well. Okay, so we have those two tables. Now let's actually start with those, and let's make sure that they work. So there's our first one, and here's our second series. Great. Now what I'm going to do is actually insert some data. We'll come back to reviews in a moment. So I have a bunch of series data here. You can, of course, copy and paste it from the included code, which is what I recommend you doing because this took forever to type. Although it's not as bad. I'll give you a preview of what our reviews data looks like. That was a pain to type. So this isn't as bad. But we've got shows. Most of them are shows that I picked because I like, but I also picked some because I didn't like them, so that we have some variation and in the ratings in particular. I wanted to make sure that our data was realistic and not everything was a 9.0. So I'm just going to copy this over, put it in this file so we have a record of it, and I'm going to insert it and make sure it works. Okay, so that was 14 series we just inserted, and I'll do the same thing for reviewers. We only have 7 here, but that's plenty. And we'll paste it in. Now let's make sure it works. Let's do a select star from series to start. You can see, if I make this a bit bigger, here's all of our series. Archer, Arrested Development, Bob's Burgers, all the way down. We've got animation, comedy, and dramas. And then let's do a select star from reviewers. And we've got 7 of them, totally random names, except I did put myself in there purely so that I could review my own shows that I like. Everyone else has fictional, just totally made up reviews, but the ones that I put in there are relatively accurate to my personal TV tastes. Okay, so then that leaves us with having to now implement the reviews table, which we left for last because, for one thing, it depends on these 2 tables, and it's also a little bit more complicated. So let's get started. Scroll back up. I like to do all of our kind of schema code up top. So we'll create table, and this is reviews. And the first part's easy, or easy enough. We'll have an ID, which is an int, auto increment primary key. And then the next part's pretty simple too, which is rating. Now, what data type do we want rating to be? If we look at the examples I've given you, we have 8.9, 9.5. So we could have just done an integer, and that would work. But that's not the way that we're going to go here because we want decimals after it. So we could have just only allowed whole numbers from 1 to 10. But instead, we're going to do sort of like IMDb does, where they have a decimal system. And our maximum rating will be 9.9. So 0 to 9.9. So that's going to be a decimal. And if you think back to the section on data types, there are two things we pass into the decimal. The first is the total number of digits we want allowed, which is just 2. Because we only want things like 4.4. We don't want 43.4. We don't want 99.9. And then the second is how many things or how many numbers after the decimal place. We just want 1. So that will give us 2 total numbers, like 9.9 or 5.6, something like that. So that's all we need there. Now we get to, if we go back, series ID and reviewer ID. So both of those will just be integers. So we'll just start with that. Series ID is an int, and reviewer ID is an int as well. But of course we're not done, because now we need to explicitly say that they are foreign keys. Remember from the last section, you don't have to do that. But it's a really smart thing to do to enforce that when you insert a review, it actually corresponds to a valid series and valid review. So the syntax for this, it's been a little bit, but it's foreign key, and then we tell it, we'll work with a series ID first. So we're saying, okay, this field series ID is a foreign key, references, and what is it referencing? The series table, and what field? The ID field. So just like that. And then we'll do the same thing, but this time we're saying this reviewer ID field right here is a foreign key, references the reviewer table up here, the ID field there. Whoops, there we go. Let's make sure we have commas in the right places. Add in our semicolon at the end, and let's see if it works. So there is a mistake in this code. I've already gone back and edited this, but I kept this in here because it's a mistake that I think is pretty common. And it's a little tough to spot. If you look at, maybe you already spotted it, but if you look at the result or the error I get, it says can't create table. It's really not very useful. But what's happening here, typically if we get an error like that, it has something to do with foreign keys here. And the main thing, remember that these are referencing external tables. So we have a series table, but we don't have a reviewer singular table. It's reviewers. So I end up doing that quite often. I see some of my students do that often as well, because sometimes you just talk about things in singular. We have reviewer ID versus reviewers ID here. It's very easy to mess that up. So now, hopefully, it should work just fine. And it appears to. Okay, so we still don't have any data in there. The last thing that we'll do is copy and paste this monster, all these reviews. This was like an hour to try and get this with some realistic data. So I wanted numbers that relatively accurately reflected the quality of shows. Now, you may disagree with it, but copy this in. Definitely don't waste time typing this yourself. Copy it from the code that I've provided and paste it. Okay. So now we should be good to go. I'm just going to add this in here so we have a record of it. And just to double check that everything worked, we're just going to select star from reviews, and we'll leave it at that. So as long as we see our data in here, notice how difficult it is to understand. What does any of this really mean? At the moment, nothing, unless you happen to know, you have memorized the different IDs for series and for reviewers. So that was preparing our data, creating our schema, and inserting our sample data. Next up, we're going to start working with it. All right, welcome to the next section. So we're continuing on the similar path, talking about relationships, talking about joins, more complex data, multiple tables, and connecting those tables, drawing lines between them. However, we're now moving on to our next relationship, which is the many-to-many relationship. So we saw how to do a one-to-many, which is a pretty standard relationship, and it's pretty common. Many-to-many is common as well, maybe not as common, but still very, very common. So we're going to see how to do it, and the reason that I saved it for last is that it's a little bit trickier. It's not hard, I don't want to scare you away, but you'll see there's a little more setup involved. And then once we've discussed on a high level how many-to-many relationships typically work. We're going to implement one using some relatively complex data that I spent way too long creating, and then we'll do some problems together. So this section will actually serve more as a code along. So I would encourage you, if you don't typically, I encourage you to follow along. We're going to use some relatively complex data, like I said, and we'll just go through it, do a couple exercises together, and I'm going to use it as a way to illustrate how joins work on a many-to-many relationship. So let's start in this video just by talking about the many-to-many relationship. So we kind of discussed it briefly in the last section, but here are a couple examples. So books and authors. Harkening back to that last section where we saw books, a book can have multiple authors, right? There are lots of books that are written by co-authors or teams of, if it's a collection, if it's an anthology, there might be 20 authors. And each of those authors can then have multiple books. So it's a many-to-many relationship. Books can have many authors. Authors can have many books. Or another common example is blog post or some sort of content, whether it's an Instagram photo, a Tumblr, whatever you call it, a Tumblr post, or just a traditional blog, some sort of content, and then tags. Tags, by that I mean things like, sunset picture, or there's some really silly, like van life, if you're familiar with that hashtag. Or I do a lot of photography, so I see a lot of tags that are things like masterpiece landscape photography, and then Insta good if you use Instagram. There's all these different tags that are out there, and each post can have multiple tags. So there's a limit sometimes, but on Instagram you can have 30 hashtags, I think it is, on a photo, and then each of those tags can then have as many posts or photos as necessary. So that's another example. And the final example I have here is students in classes. So we're talking about like maybe college students or university students, where students have multiple classes. They pick their classes at the beginning of the semester. One student usually must have multiple classes, unless maybe it's your last semester, but you have multiple classes that you go to, that you're related to, and then each class is going to have multiple students in it. And that's a many-to-many relationship. And the one that we'll be working with in this section is actually not listed here. It's a little different. And to start off, I want you to imagine that we're building a TV show reviewing application. Like, yes, I know we don't need any more of those, but imagine something like Internet Movie Database. Very, very simple version though. But we're working with TV shows exclusively. And the key idea is that we can have someone who signs up as a reviewer. We can have TV shows that, let's say some of the ones I'm using, Fargo, the TV show, Archer, General Hospital, any series, and a reviewer can then rate any of those series. So I could sign up and rate Archer as a 8.5 out of 10. So to accomplish this relationship, a many-to-many relationship, where we're basically associating users, or reviewers we'll call them, with TV shows, we need to actually use 3 tables. We use what's known as a join table or a union table. So we have our series data up here. So these would be the TV shows. And then down here, we have our reviewers data. So these would be just names in our case. We'll keep it very simple. This will be Colt, or this will be Charlie, or whatever it is. But the way that they're connected is through a third table, through a reviews table. So this will make sense when I show you the schema in just a moment. But think about it this way. Series exist on their own. They're just TV shows. Reviewers exist on their own. They have nothing to do with a series out of the box. It's just someone's name. But they then are associated through this reviews table. So this reviews table will have information on the TV show that's being reviewed, and then the reviewer who is doing it, as well as a third piece of information, which is the rating. What's the number, the numeric representation of that review? So without further ado, let's take a look at our schema. We have 3 tables. Reviewers over here with an ID, primary key, first name and last name. And of course, in a real application, we would have more data here, right? We would have email. We'd be storing our password in a safe, protected way. We would have things like registration date, maybe last active, all that kind of stuff. But to keep it simple here so we can focus on the relationship, focus on the joins, I'm only doing first name and last name. Then we also have series. And, this is something I actually debated. The plural of series in English, modern, traditional, spoken English, is just series. However, a lot of people would argue that we should name this table series with an ES on the end, just to make it clear that that's the table name. I'm not exactly a fan of that. It's really determined by the project or the team you're working with, or by you if you're working on your own thing. I've worked on projects where we had to abide by that, where the plural was always with an S afterward, even if that meant mouses instead of mice. But I'm going to leave it as series just because I think it's simplest. So series has a primary key ID, a title, so that would be Fargo, which is a TV show as well, really good TV show actually, not just a movie. So Fargo or Halt and Catch Fire, Seinfeld, and then the release year. So 2014 or 2002 or whatever it is. And then a genre, which we're going to keep very simple. We're only going to have animation, comedy, and drama. So just a couple of examples of genres. But again, these on their own are just separate entities. Where they're joined is through this third reviews table, which is what's known as a join or union table. It's connecting these two. And the way it's doing that, well, first of all, it has an ID. Nothing special there. Every review has an ID. There's a rating. So this would be, 5.0 for a mediocre show, or 9.9 for a fantastic show. And then the series ID. So that's going to be a foreign key pointing to the series table. So what series? Is this Fargo? Is this Seinfeld? And then the same, well, not the exact same, but the same idea for reviewer ID. It's going to be a foreign key pointing to the reviewer's table, the ID field. So then a single review will have an ID, it will have a rating, 9.0, a series ID, like 1, and then a reviewer ID, which could also be 1. They're pointing to different tables. So this is a centralized repository or centralized place for our information to be stored. It's connecting these two tables through this table. So hopefully you can see how this is going to work. Basically, reviews on its own is going to be a pretty ugly table to look at. It's just going to be numbers. It will have an ID, which is a number. Rating is a number. Series ID is a number, and reviewer ID is a number. So looking at it on its own is actually going to be very confusing. It's not going to make sense. So we'll have to use joins to be able to understand things, so that we could use a join to replace series ID with the name of the series, so that it says Fargo instead of 1. Or it will say Blue Steel instead of reviewer ID 3, and so on. So that's our basic idea here. Here's an example with some simple data. Very, very simple, 2 reviewers. So we've got Blue Steel and Wyatt Earp, ID of 1 and 2. Then we've got 2 series, Archer and Fargo. If you're not familiar with these shows, don't worry. That's not necessarily relevant. Archer is animation, released first in 2009. Fargo is a drama with a little comedy, released in 2014. Archer has ID of 1. Fargo has ID of 2. So they're independent. But then our reviews table. Well, somebody reviewed something with a rating of 8.9. The person who did that has a reviewer ID of 1. So that is Blue Steel. So Blue Steel reviewed something and gave it an 8.9. Well, what did she review? Whatever has series ID 2. So Fargo. So Blue gave Fargo an 8.9. Then we have a 9.5 down here, and the reviewer ID is 2. So that's Wyatt Earp, this field or this row here in reviewers. Wyatt Earp also reviewed Fargo because it's ID 2. As we can see, corresponds to Fargo. So essentially what we're storing here, Fargo has been rated twice. Once by Blue as an 8.9 and once by Wyatt as a 9.5. So as you can see, the data is not that pretty in this table, and this is only with 2 reviews. We'll be working with somewhere around 100 reviews, which is a lot of data to look at on its own. And so we'll really be focusing on making that data understandable, readable, which is really the point of this entire exercise. So we're pretty much done here in this first video. We didn't actually do anything except discuss our schema. But in the next video, we'll actually go about implementing the tables and inserting some data on our own. Hey, welcome to the next section. So I'd like to start off this section by asking you a question. It's not really a quiz or anything, but I just want to know why there's a chicken on my desk. And in the meantime, Blue and I are here to talk to you about the next section. So we're continuing on our trend of working with multiple tables. We saw a one-to-many relationship in the last section. Now we're moving on to a many-to-many relationship. And I saved this one for second. It's a little more complex. Don't be afraid. It's still very doable and very important. I keep saying that. Very useful to be able to have multiple tables with a many-to-many relationship. So we're going to focus on this section on implementing a schema for TV shows with reviewers and the reviews that they write. So think of Breaking Bad and American Horror Story are two different shows. We'll have a bunch of them. I'll give you data. And then 10 different human reviewers, maybe a cat or two as well. And these reviewers can go and assign ratings to every show. So I could say, this is a 10, that's a 9, that's a 4, whatever. So that's what we're going to implement, that sort of a schema, which is a many-to-many relationship. Hey. Stop eating that. Eat the chicken. So, okay, where was I? Exercises, yes. This section is all exercise, basically. The way that I decided to do it is to go through not only building the schema, but also asking common questions about the data and performing common operations and the joins we want to perform basically as we go. So the whole thing acts as a bit of a code-along / exercise. So hopefully you like television. If you don't, then this will be a great insight, great window into the world of television for you. But more importantly, we're talking about joins again, working with multiple tables. All right.